take a deep breath. The universe is vast, and tonight we are exploring it together. There are places in the cosmos where the rules we know, the ones that govern falling apples and orbiting planets, are pushed so far beyond their limits that they break down entirely. Where gravity becomes so overwhelming that nothing, not even light itself, can escape. Where a teaspoon of matter weighs as much as a mountain. Where time, as we experience it, slows to a crawl and then stops altogether at an invisible boundary we call the event horizon. Tonight, we are descending into the most extreme environments the universe has ever created: neutron stars and black holes. These are not distant abstractions. They are real objects forged in the violent depths of massive stars, and they represent gravity's final word on what matter can become. We will begin with the life cycle of stars, how they burn, how they balance, and how they die. From there, we will witness the catastrophic collapse that creates a neutron star, an object so dense that atomic structure itself is crushed into oblivion. And then we will go further, past the neutron star, past the point where even neutrons cannot resist. We will approach the event horizon of a black hole, where space-time curves so steeply that it folds in on itself, and we will try to understand what happens when matter crosses that threshold and vanishes from our universe forever. This is not a journey for the faint of heart, but it is one we will take slowly, carefully, and together. The physics is dense, but it is also beautiful. And by the end, you will understand why these objects are not just cosmic curiosities. They are the keys to understanding the very fabric of reality. If these quiet explorations help you rest, or if they satisfy a curiosity you have carried with you, please consider liking and subscribing. It helps others find their way here, to this quiet place between the stars. Now, let us begin. Close your eyes if you wish. Settle into the darkness, and let us travel to the edge of everything we know. Somewhere in the galaxy, a star is dying. Not the gentle fading of a star like our sun, which will shed its outer layers over billions of years and settle into a quiet white dwarf. This is something far more violent, far more consequential. This is a star with 15 times the mass of the sun, and it has been burning through its nuclear fuel at a furious pace for only 10 million years. Now, in the final hours of its existence, the physics of gravity and nuclear fusion are about to collide in one of the most energetic events the universe can produce. For most of its life, this massive star maintained a delicate equilibrium. Deep in its core, hydrogen nuclei fused into helium at temperatures exceeding 15 million Kelvin, releasing energy in the form of gamma radiation. This energy pushed outward, creating what physicists call radiation pressure, and it balanced perfectly against the inward pull of gravity from the star's enormous mass. For millions of years, this balance held. The star burned steadily, converting roughly 600 million tons of hydrogen into helium every single second. But hydrogen is finite. When the core exhausted its hydrogen supply, the fusion reaction slowed, and gravity gained the upper hand. The core contracted, compressing and heating until it reached 100 million Kelvin, hot enough to ignite helium fusion. Helium nuclei, each containing 2 protons and 2 neutrons, began slamming together to form carbon and oxygen. The star found a new equilibrium, but this fuel burned faster. Where hydrogen fusion sustained the star for 10 million years, helium fusion lasted only 1 million. The pattern repeated with increasing urgency. Carbon ignited at 600 million Kelvin, fusing into neon, sodium, and magnesium over the course of 1,000 years. Neon burned at 1.2 billion Kelvin, lasting perhaps a single year. Oxygen fusion followed at 2 billion Kelvin, producing silicon and sulfur in a matter of months. And finally, silicon began fusing at 3 billion Kelvin, creating iron, nickel, and cobalt in the core. This final stage lasted approximately 1 day. The star now resembles an onion, with concentric shells of different elements surrounding the core. The outermost layer still contains hydrogen. Beneath it lies helium, then carbon, neon, oxygen, silicon, and at the very center, a ball of iron roughly the size of Earth, but containing 1.4 solar masses of material. The density here reaches 400 billion kilograms per cubic meter, millions of times denser than any material on Earth. Iron is the end of the line. Every fusion reaction before this point released energy because the products weighed slightly less than the reactants, and that missing mass converted to energy according to Einstein's famous equation. But iron sits at the bottom of the nuclear binding energy curve. Fusing iron into heavier elements does not release energy. It requires energy. The core has built a dead end, an ash heap of nuclear fusion, and it can no longer generate the outward pressure needed to support the star. The collapse begins almost instantaneously. Without radiation pressure to oppose it, gravity compresses the iron core at velocities approaching 70,000 kilometers per second, roughly a quarter of the speed of light. In less than 1 second, the core shrinks from the size of Earth to a sphere only 30 kilometers across. The density skyrockets to 400 trillion kilograms per cubic meter, exceeding the density of an atomic nucleus. At these extreme conditions, matter behaves in ways that seem almost impossible. Electrons are squeezed so tightly against protons that they combine through a process called electron capture, producing neutrons and releasing neutrinos. The core transforms from a ball of iron nuclei and electrons into a sea of neutrons packed together like marbles in a jar. This process, called neutronization, releases an enormous flood of neutrinos, ghostly particles that barely interact with matter. In a single second, the collapsing core emits more energy in neutrinos than the Sun will produce in its entire 10 billion year lifetime. The outer layers of the star, still containing several solar masses of material, are falling inward at tens of thousands of kilometers per second. They do not yet know that the core has collapsed. Information cannot travel faster than the speed of sound in the stellar material, and the collapse happened so quickly that the outer layers are still in free fall when the core reaches its maximum compression. At the center, the neutrons resist further compression through a quantum mechanical effect called degeneracy pressure. Neutrons are fermions, particles that obey the Pauli exclusion principle, which forbids two identical fermions from occupying the same quantum state. When packed this tightly, the neutrons exert an outward pressure not from thermal motion, but from the fundamental rules of quantum mechanics. The core stiffens, becoming nearly incompressible, and the infalling material slams into this newly rigid surface at a significant fraction of the speed of light. The collision creates a shock wave that propagates outward through the star. Behind the shock, temperatures exceed 50 billion Kelvin, hot enough to tear apart atomic nuclei through a process called photodisintegration. The shock loses energy as it climbs outward, and for a moment, it stalls roughly 200 kilometers from the center, unable to push through the still-in-falling outer layers. This is where the neutrinos become crucial. Although neutrinos interact only weakly with matter, the densities in the region just behind the shock are so extreme that even a tiny fraction of the neutrino energy gets absorbed. This energy deposition, occurring over a few hundred milliseconds, revives the stalled shock and drives it outward with renewed force. The mechanism is subtle, involving complex fluid dynamics and neutrino transport, and supercomputer simulations running for months are required to model it accurately. The shock accelerates, tearing through the silicon and oxygen shells, then the carbon, helium, and hydrogen layers. Within hours, it reaches the stellar surface and explodes outward into space. The star brightens by a factor of 10 billion, briefly outshining its entire host galaxy. This is a core collapse supernova, specifically a Type II supernova, and it will remain visible across intergalactic distances for weeks. Behind the expanding debris cloud, something remains. The collapsed core, now a ball of neutrons roughly 20 kilometers in diameter, spins rapidly due to conservation of angular momentum. If the original core rotated once per month, the compressed remnant might spin dozens of times per second. Its magnetic field, amplified by the compression, reaches strengths of 100 million Tesla, trillions of times stronger than Earth's magnetic field. The surface temperature exceeds 100 billion Kelvin in the first seconds after formation, though it will cool rapidly by emitting neutrinos. This is a neutron star, one of the densest objects in the known universe. A teaspoon of its material would weigh approximately 6 billion tons on Earth, equivalent to the mass of a small mountain compressed into a volume smaller than a sugar cube. The gravitational field at its surface is roughly 200 billion times stronger than Earth's gravity, strong enough that an object dropped from 1 meter would impact the surface at over 2 million meters per second. The supernova explosion scatters heavy elements into the interstellar medium. The silicon, oxygen, carbon, and iron forged in the star's core, along with heavier elements like gold, platinum, and uranium created in the extreme conditions of the explosion itself, will eventually mix with hydrogen clouds and form new stars and planets. Every atom of iron in your blood, every atom of calcium in your bones was forged in a star like this one and scattered by a supernova explosion billions of years ago. The debris expands at thousands of kilometers per second, glowing brightly in optical, X-ray, and radio wavelengths. Over thousands of years, it will form a supernova remnant, a shell of hot gas and tangled magnetic fields. The Crab Nebula, visible in the constellation Taurus, is the remnant of a supernova observed by Chinese astronomers in the year 1054. At its center lies a pulsar spinning 33 times per second, the compressed core of a star that died nearly 1,000 years ago. But not every dying star leaves behind a pulsar. Not every stellar corpse becomes a neutron star. The fate of a star's core depends on a single, critical factor: its mass. and the boundary between one destiny and another was discovered not through telescopes or explosions, but through the quiet mathematics of a 19-year-old physicist sailing from India to England in 1930. Subrahmanyan Chandrasekhar spent his voyage across the Arabian Sea calculating what happens inside a white dwarf, the dense remnant left behind when a star like our Sun exhausts its nuclear fuel. He combined two of the great theories of 20th century physics: Einstein's special relativity and the newly developed quantum mechanics. What he found would earn him a Nobel Prize 53 years later and would forever change our understanding of stellar death. To understand his discovery, we must first understand what holds a white dwarf up against its own gravity. When a star like the Sun runs out of hydrogen fuel in its core, it cannot sustain the nuclear fusion that has balanced gravitational collapse for billions of years. The core contracts, and as it shrinks, something remarkable happens. The electrons within the core, stripped from their atoms by the intense heat, begin to resist further compression through a purely quantum mechanical effect. This resistance has nothing to do with electrical repulsion or thermal pressure. It arises from a fundamental principle of quantum mechanics discovered by Wolfgang Pauli in 1925. No two electrons can occupy the same quantum state simultaneously. This is the Pauli exclusion principle, and its consequences for dying stars are profound. As the core contracts and electrons are squeezed closer together, they are forced into higher and higher energy states because the lower states are already occupied. These high-energy electrons exert an outward pressure even at absolute zero temperature, a pressure that depends only on density, not on heat. This is electron degeneracy pressure, and it is what supports a white dwarf against gravitational collapse. A white dwarf is an extraordinary object. The core of a star that once spanned hundreds of thousands of kilometers has been compressed into a sphere roughly the size of Earth, perhaps 12,000 kilometers in diameter. Yet it contains a mass comparable to the Sun, about 200,000 times the mass of Earth, packed into a volume 1 million times smaller. The density at the center of a typical white dwarf reaches approximately 1 million grams per cubic centimeter. A teaspoon of white dwarf material would weigh about 5 tons on Earth, as much as an elephant. At these densities, matter behaves in ways utterly unlike anything in everyday experience. The electrons are no longer bound to individual atoms. Instead, they form a degenerate gas, a quantum fluid where the electrons move freely through a lattice of atomic nuclei, primarily carbon and oxygen, for a white dwarf formed from a sun-like star. The nuclei themselves are packed so tightly that they form a crystalline structure, and as the white dwarf cools over billions of years, this crystal grows from the center outward. The core of an old white dwarf is essentially a giant diamond, a crystal of carbon atoms surrounded by a sea of degenerate electrons. But Chandrasekhar's calculations revealed something troubling. As the mass of a white dwarf increases, the electrons must be packed more tightly to provide the pressure needed to support the additional weight. At higher densities, the electrons are forced to move faster and faster, and here, Einstein's special relativity enters the picture. As electrons approach the speed of light, their behavior changes. The relationship between their momentum and energy shifts from the classical form to the relativistic form. The pressure they can exert no longer increases as rapidly with density. Chandrasekhar worked through the mathematics and found that there is a maximum mass that electron degeneracy pressure can support. Beyond this limit, no amount of electron pressure can halt gravitational collapse. This maximum mass is approximately 1.4 times the mass of the Sun. It is now called the Chandrasekhar limit, and it represents one of the most important numbers in astrophysics. A white dwarf with a mass below this limit can remain stable for trillions of years, slowly cooling and fading into darkness. But a stellar core that exceeds this mass cannot be supported by electron degeneracy pressure. Gravity wins, and the collapse continues. The value of 1.4 solar masses emerges from fundamental constants of nature: the gravitational constant, Planck's constant, the speed of light, and the mass of the proton. It is not arbitrary. It is written into the fabric of physics itself, a cosmic speed limit for the mass of degenerate matter supported by electrons. When Chandrasekhar presented his results to the Royal Astronomical Society in 1935, he was publicly ridiculed by Arthur Eddington, one of the most famous astronomers of the era. Eddington found the implications disturbing. If a star's core exceeded the Chandrasekhar limit, what would stop its collapse? Would it shrink forever? Eddington declared that there must be some law of nature preventing such an outcome, that stars would find a way to shed mass and stay below the limit. But nature is not obligated to conform to human comfort. Observations over the following decades confirmed Chandrasekhar's mathematics. White dwarfs cluster around masses between 0.5 and 1.0 solar masses, with very few approaching the limit. Those that do approach it, often by accreting matter from a companion star in a binary system, face a dramatic fate. When a white dwarf in a binary system pulls material from its companion, its mass gradually increases. As it approaches 1.4 solar masses, the density and temperature at its center rise. If the white dwarf is composed primarily of carbon and oxygen, the increasing temperature can ignite carbon fusion in a runaway thermonuclear reaction. Unlike the controlled fusion in a normal star's core, this fusion is uncontrolled because the degenerate matter cannot expand to cool itself. The temperature rises, the fusion rate increases, the temperature rises further. Within seconds, the entire white dwarf is consumed in a thermonuclear explosion that completely destroys the star. This is a Type 1a supernova, and because it always occurs at approximately the same mass, it always releases approximately the same amount of energy. About 1 to 2 times 10 to the 44th joules, equivalent to the Sun's total energy output over 10 billion years released in a few seconds. This consistency makes Type 1 a supernovae standard candles for measuring cosmic distances, and their observation in distant galaxies led to the 1998 discovery that the expansion of the universe is accelerating. But not all cores that exceed the Chandrasekhar limit explode. In the iron cores of massive stars, the situation is different. There is no fuel left to burn, no thermonuclear explosion to disperse the star. Instead, gravity simply overwhelms electron degeneracy pressure, and the collapse continues to even more extreme densities. The electrons are squeezed so tightly that they are forced to combine with protons through a process called electron capture, or inverse beta decay. Each electron merges with a proton to form a neutron and a neutrino. The neutrino escapes, carrying away energy, while the neutron remains behind. As the collapse proceeds, the core transforms from a sea of electrons and nuclei into a sea of neutrons. A new form of pressure emerges, neutron degeneracy pressure, governed by the same Pauli exclusion principle but now applied to neutrons rather than electrons. This pressure can halt the collapse, but only if the core's mass is below another critical threshold, the Tolman-Oppenheimer-Volkoff limit, approximately 2 to 3 solar masses depending on the equation of state of nuclear matter. The transition from white dwarf to neutron star represents a compression by a factor of about 1,000 in radius. A white dwarf the size of Earth becomes a neutron star the size of a city, perhaps 20 kilometers across. The density increases from 1 million grams per cubic centimeter to several hundred million tons per cubic centimeter. At these densities, atomic nuclei merge and dissolve, and matter takes on properties found nowhere else in the observable universe. The collapse happens in less than a second. After millions of years of steady nuclear burning, after the careful construction of an iron core over thousands of years, the final gravitational implosion takes approximately 1/4 of a second. The core, roughly the mass of the Sun, falls inward at speeds approaching 70,000 kilometers per second, nearly a quarter of the speed of light. This is the fastest large-scale motion that occurs anywhere in the universe outside of relativistic jets and particle accelerators. As the inner core collapses, it compresses beyond the point where electron degeneracy pressure can provide support. Electrons are forced into protons through a process called electron capture, or inverse beta decay. Each proton absorbs an electron and transforms into a neutron, releasing a neutrino in the process. The reaction is simple in its chemistry but staggering in its scale. Approximately 10 to the power of 57 neutrinos are produced in the span of a few seconds, carrying away roughly 3 times 10 to the power of 46 joules of energy. This is more energy than our Sun will produce in its entire 10 billion-year lifetime, released in a burst lasting perhaps 10 seconds. The inner core continues to fall until it reaches nuclear density, approximately 2.3 times 10 to the power of 17 kilograms per cubic meter. At this density, the strong nuclear force becomes repulsive at short range, and neutron degeneracy pressure activates. The inner core, now a proto-neutron star, perhaps 40 kilometers across, suddenly stiffens. It becomes nearly incompressible, like a ball of nuclear matter that refuses to shrink further. The outer core, still falling inward at tens of thousands of kilometers per second, slams into this suddenly rigid inner core. The collision generates a shock wave that propagates outward through the still infalling material. This is the bounce, the moment when gravitational collapse reverses direction at the boundary between the inner and outer core. The shock wave carries enormous energy, initially around 10 to the power of 44 joules, and begins to push outward against the rain of iron and silicon still falling from above. But the shock wave faces a problem. As it moves outward through the infalling material, it must heat that material and break apart iron nuclei through a process called photodisintegration. Each iron nucleus requires approximately 8.8 million electron volts to disassemble into free protons and neutrons. The shock wave spends its energy on this nuclear demolition, and within milliseconds, it stalls. The shock front stops expanding, hovering at a radius of perhaps 100 to 200 kilometers from the center, neither advancing nor retreating. The supernova, it seems, has failed before it truly began. This is the stalled shock problem, and it puzzled astrophysicists for decades. The bounce alone does not provide enough energy to blow the star apart. Something else must revive the shock and push it through the remaining stellar envelope. The answer lies in those 10 to the power of 57 neutrinos streaming outward from the proto-neutron star. Neutrinos interact only weakly with matter. A single neutrino could pass through a light year of solid lead with only a 50% chance of being absorbed. Under normal circumstances, they are essentially invisible to ordinary matter. But the conditions behind the stalled shock are far from normal. The density reaches 10 to the power of 12 kilograms per cubic meter, and the neutrino flux is so intense that even with their tiny interaction cross-section, a small fraction of them deposit their energy into the material just behind the shock front. This region, called the gain region, absorbs perhaps 1% of the outgoing neutrino energy. 1% of 3 times 10 to the power of 46 joules is still 3 times 10 to the power of 44 joules, enough to revive the shock and drive it outward. The process is called neutrino heating, and it operates over a time scale of hundreds of milliseconds. The shock wave, reinvigorated by this continuous energy deposition, begins to accelerate outward through the star. The revival is not smooth or symmetric. Convection develops behind the shock, with hot bubbles of neutrino-heated material rising outward while cooler material sinks back toward the proto-neutron star. This convective overturn, combined with a fluid instability called the standing accretion shock instability, creates asymmetries in the explosion. The shock wave does not expand as a perfect sphere, but rather as a turbulent, lumpy surface, with some regions moving faster than others. These asymmetries have observable consequences. The proto-neutron star receives a gravitational kick from the uneven explosion, accelerating to velocities of hundreds of kilometers per second. Pulsars, the spinning neutron stars left behind by supernovae, are observed to move through space at average speeds of 400 to 500 kilometers per second, with some reaching over 1,000 kilometers per second. These velocities are imparted in the first seconds of the explosion, a testament to the violence of the asymmetric shock revival. As the shock wave propagates outward, it encounters the successive layers of the star, each with its own composition: the silicon shell, the oxygen shell, the neon, carbon, and helium layers, and finally the hydrogen envelope if one remains. The shock heats each layer to temperatures of several billion Kelvin, triggering explosive nuclear burning. Silicon burns to iron group elements in a process called explosive silicon burning. Oxygen burns to silicon and sulfur. These reactions add energy to the shock and synthesize heavy elements that will eventually be scattered into the interstellar medium. The passage of the shock through the star takes hours to days, depending on the stellar radius. For a blue supergiant with a radius of perhaps 50 solar radii, the shock reaches the surface in a few hours. For a red supergiant with a radius of 1,000 solar radii, the journey takes a day or more. When the shock finally breaks through the stellar surface, the supernova becomes visible. The sudden release of radiation produces a flash of ultraviolet and X-ray light called the shock breakout, lasting only minutes, but carrying diagnostic information about the explosion dynamics. The optical light curve that follows is powered by different mechanisms at different times. In the first days, the expanding and cooling ejecta radiate the thermal energy deposited by the shock. Later, the light curve is sustained by the radioactive decay of nickel-56 synthesized in the explosion. Nickel-56 has a half-life of 6.1 days and decays to cobalt-56, which in turn decays to stable iron-56 with a half-life of 77 days. A typical core collapse supernova produces between 0.01 and 0.1 solar masses of nickel-56, and the gamma rays from its decay are thermalized by the expanding ejecta, keeping the supernova visible for months. The total energy released in a core collapse supernova is approximately 3 × 10 to the power of 46 joules. But only about 1% of this energy goes into the kinetic energy of the ejecta, roughly 10 to the power of 44 joules. An even smaller fraction, perhaps 10 to the power of 42 joules, emerges as visible light. The vast majority of the energy, 99%, is carried away by neutrinos, invisible to optical telescopes but detectable by specialized neutrino observatories. On February 23, 1987, neutrino detectors in Japan and the United States recorded a burst of approximately 25 neutrinos over a span of 13 seconds. These neutrinos came from supernova 1987A in the Large Magellanic Cloud, 168,000 light-years away. This detection confirmed the basic picture of core collapse supernovae and marked the birth of neutrino astronomy for sources beyond our solar system. Those 25 neutrinos, detected across 2 continents in the span of 13 seconds, carried information about a transformation occurring 168,000 years before their arrival. At the center of that distant explosion, in the heart of supernova 1987A, matter was undergoing a change so profound that it would create an entirely new state of existence. The collapsing core, having bounced and launched the supernova shock, was settling into its final form. It was becoming a neutron star. The process begins with a phenomenon called neutronization, sometimes referred to as inverse beta decay. Under normal conditions, a free neutron is unstable. Left alone, it will decay into a proton, an electron, and an antineutrino within about 15 minutes. But in the crushing environment of a collapsing stellar core, the opposite reaction becomes favorable. Electrons are forced into protons with such violence that they merge, producing neutrons and neutrinos. The reaction can be written simply: a proton plus an electron yields a neutron plus an electron neutrino. This process strips the core of its electrons and converts its protons into neutrons, one collision at a time. The conditions required for this transformation are extreme beyond ordinary experience. The density must exceed approximately 4 × 10 to the 11th kilograms per cubic meter, roughly 400 billion kilograms packed into a space the size of a sugar cube. At these densities, electrons are squeezed so tightly that their quantum mechanical pressure can no longer support the weight of the overlying material. The electrons have nowhere to go except into the atomic nuclei themselves, where they combine with protons and vanish from the electron population entirely. Consider what this means for the matter involved. An iron nucleus contains 26 protons and typically 30 neutrons. As the collapse proceeds and neutronization accelerates, those 26 protons are gradually converted. The nuclei become increasingly neutron-rich, passing through configurations that would be wildly unstable under normal circumstances. Iron becomes manganese, becomes chromium, becomes vanadium, but these are not the familiar isotopes found in laboratories. These are exotic, neutron-bloated versions that exist only in the hearts of dying stars. The temperature during this phase reaches approximately 100 billion Kelvin, 10,000 times hotter than the core of our Sun. At these temperatures, photons carry enough energy to shatter atomic nuclei through a process called photodisintegration. The carefully constructed iron nuclei, built over thousands of years of silicon burning, are torn apart into their constituent protons, neutrons, and alpha particles. This destruction absorbs energy, roughly 8.8 million electron volts per nucleon, accelerating the collapse by removing thermal pressure support. The neutrinos produced during neutronization carry away energy at a staggering rate. In the first few seconds after core bounce, the proto-neutron star radiates approximately 3 times 10 to the 53 ergs in neutrino luminosity. This is roughly 100 times the total energy output of all the stars in the observable universe during that same interval. The neutrinos stream outward at nearly the speed of light, passing through the overlying stellar material as if it were transparent, though even they experience some scattering in the densest regions. As the neutronization proceeds, the core contracts further. A mass of approximately 1.4 solar masses, the Chandrasekhar limit that marked the end of white dwarf stability, is now compressed into a sphere roughly 20 kilometers in diameter. The density at the center reaches 2 to 3 times 10 to the 17th kilograms per cubic meter. At this density, a teaspoon of neutron star material would weigh approximately 6 billion tons, more than the combined mass of every human being who has ever lived, multiplied by a factor of nearly 1,000. The gravitational field at the surface of this newborn neutron star is correspondingly intense. The surface gravity reaches approximately 2 times 10 to the 12th meters per second squared, roughly 200 billion times the gravitational acceleration at Earth's surface. An object dropped from a height of 1 meter above a neutron star surface would strike that surface traveling at approximately 2 million meters per second, a significant fraction of the speed of light. The escape velocity from the surface exceeds 100,000 kilometers per second, roughly 1/3 the speed of light. The compression does not stop at nuclear density. In the innermost regions of the core, the density may exceed the density of atomic nuclei themselves, reaching perhaps 5 to 10 times 10 to the 17th kilograms per cubic meter. At these densities, the distinction between individual neutrons begins to blur. The neutrons overlap, their wave functions interpenetrating, creating a state of matter that exists nowhere else in the present-day universe except inside neutron stars and during the first microseconds after the Big Bang. This matter is supported against further collapse by neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being squeezed into the same quantum state. Like electron degeneracy pressure in white dwarfs, neutron degeneracy pressure arises from the Pauli exclusion principle, which forbids identical fermions from occupying identical quantum states. But neutrons are nearly 2,000 times more massive than electrons, so they can be packed much more tightly before their degeneracy pressure becomes significant. This is why neutron stars are so much smaller and denser than white dwarfs. The newborn neutron star is not yet in equilibrium. It is hot, with internal temperatures exceeding 50 billion Kelvin, and it is still contracting as it radiates away its thermal energy through neutrino emission. This cooling phase, called the Kelvin-Helmholtz epoch, lasts approximately 10 to 100 seconds. During this time, the proto-neutron star shrinks from an initial radius of perhaps 50 kilometers to its final radius of 10 to 15 kilometers. The neutrino luminosity gradually decreases as the star cools and becomes more transparent to neutrinos. The contraction during cooling has a remarkable consequence for the star's rotation. The original stellar core, before collapse, might have been rotating with a period of several hours or even days. As it contracts by a factor of 10,000 or more in radius, conservation of angular momentum demands that its rotation rate increase by a similar factor. A core that rotated once per day before collapse will rotate hundreds of times per second afterward. The fastest known pulsar, PSRJ 1748-2446 AD, spins at 716 rotations per second, its surface moving at nearly 1/4 the speed of light. The magnetic field undergoes a similar amplification. A typical massive star might have a surface magnetic field of a few Gauss, comparable to Earth's field. As the core collapses and its radius decreases by a factor of 10,000, the magnetic flux is conserved but concentrated into a much smaller area. The magnetic field strength increases by the square of the compression factor, potentially reaching 10 to the 12 or 10 to the 13 Gauss at the neutron star surface. This is roughly 1 trillion times stronger than the strongest magnets ever produced in human laboratories. The combination of rapid rotation and intense magnetic field creates a powerful electromagnetic dynamo. The rotating magnetic field generates electric fields that can accelerate charged particles to relativistic energies. These particles stream along the magnetic field lines, emitting radiation as they go. If the magnetic axis is tilted relative to the rotation axis, this radiation sweeps across space like the beam of a lighthouse. When the beam crosses our line of sight, we detect a pulse of radio waves, X-rays, or gamma rays. The neutron star has become a pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish at Cambridge University. The signal, designated PSRB 1919+201, arrived with such precise regularity, one pulse every 1.337 seconds, that the discoverers initially considered the possibility of an artificial origin. They nicknamed the source LGM1 for Little Green Men. But the discovery of additional pulsars with different periods quickly established that these were natural objects, and the connection to rotating neutron stars was made within months. The birth of a neutron star is thus not merely a gravitational event, but an electromagnetic one as well. The collapse concentrates not only mass, but also angular momentum and magnetic flux, creating an object that radiates energy across the electromagnetic spectrum. The Crab pulsar, born in the supernova of 1054 CE, still spins 30 times per second and powers the surrounding nebula with a luminosity of approximately 200,000 times that of our Sun. After nearly 1,000 years, it continues to announce its presence across the galaxy. The Crab pulsar, spinning in its cocoon of expanding debris, appears from a distance as a point of light pulsing with metronomic precision. But that point of light conceals a structure of extraordinary complexity, a layered object where matter exists in states found nowhere else in the observable universe. To understand what lies beneath the surface of a neutron star requires a journey inward, through regions where the physics changes dramatically with each kilometer of depth. The outermost layer of a neutron star is its atmosphere, though this word carries a meaning utterly unlike anything on Earth. This atmosphere extends perhaps a centimeter above the surface, sometimes less, and consists of hydrogen, helium, or heavier elements depending on the star's history and whether it has accreted material from a companion. The temperatures here reach approximately 1 million Kelvin, hot enough that the atmosphere radiates primarily in X-rays rather than visible light. Despite these extreme temperatures, the atmosphere remains incredibly thin because the surface gravity is so intense. A neutron star with a mass of 1.4 solar masses and a radius of 10 kilometers possesses a surface gravity approximately 200 billion times stronger than Earth's. An object falling from a height of 1 meter would strike the surface at roughly 2 million meters per second, or about 0.5% of the speed of light. Beneath this tenuous atmosphere lies the outer crust, a layer perhaps a few hundred meters thick, where matter organizes itself into a crystalline lattice. Here, iron nuclei and other heavy elements arrange themselves in a regular pattern, their positive charges balanced by a sea of electrons that flow freely between them. The density at the top of this crust is approximately 1 million grams per cubic centimeter, roughly the density of a white dwarf star. But this is merely the beginning. With each meter of depth, the pressure increases and the density climbs, compressing the crystalline structure ever more tightly. As the density rises beyond approximately 400 billion grams per cubic centimeter, something remarkable occurs. The electrons, squeezed by the immense pressure, begin to merge with protons in the atomic nuclei through a process called inverse beta decay. Each merger produces a neutron and releases a neutrino that escapes the star entirely. This process, the same neutronization that occurred during the initial collapse, continues gradually throughout the inner crust, transforming the matter into increasingly neutron-rich nuclei. Elements that would be wildly unstable under normal conditions become the dominant form of matter here. Nuclei with ratios of neutrons to protons that would cause instant decay in any terrestrial laboratory. The inner crust extends from roughly 400 meters to perhaps 1 kilometer below the surface, depending on the star's total mass. In this region, the neutron-rich nuclei become so bloated with neutrons that some begin to leak out, forming a fluid of free neutrons that permeates the spaces between the nuclei. This marks the beginning of the neutron drip regime, where matter transitions from a crystalline solid to something far stranger. The nuclei themselves begin to deform under the pressure, stretching and merging into elongated shapes that physicists have given whimsical names: nuclear pasta. The nuclear pasta phase represents one of the most exotic states of matter theorized to exist. At densities around 100 trillion grams per cubic centimeter, the competition between nuclear forces and Coulomb repulsion produces structures that resemble various types of Italian cuisine. Gnocchi-like spherical nuclei give way to spaghetti-like cylindrical rods of nuclear matter. These rods then merge into lasagna-like flat sheets. As density increases further, the geometry inverts. Cylindrical holes form in the nuclear matter, creating anti-spaghetti configurations, followed by spherical holes known as anti-gnocchi or Swiss cheese phases. These structures may extend for only a few hundred meters, but they contain more mass than our entire sun compressed into a layer thinner than the depth of Earth's oceans. The transition from crust to core occurs at approximately 1 kilometer below the surface, where the density reaches roughly 200 trillion grams per cubic centimeter, about half the density of normal atomic nuclei. Here, the individual nuclei dissolve entirely, and matter becomes a continuous fluid of neutrons with a small admixture of protons and electrons. This outer core extends from 1 kilometer to perhaps 9 kilometers in depth, comprising the bulk of the neutron star's volume. The neutrons in this region exhibit a property that seems almost paradoxical given the extreme conditions. They form a superfluid. At temperatures below approximately 1 billion Kelvin, which sounds enormous but is actually quite cold by neutron star standards, the neutrons pair up through an attractive component of the nuclear force. These paired neutrons, called Cooper pairs, behave collectively as bosons and can flow without any friction whatsoever. A superfluid vortex, once established, will continue spinning indefinitely. The entire outer core of a neutron star thus rotates not as a rigid body, but as a collection of quantized vortices, each carrying a precise amount of angular momentum determined by quantum mechanics. The protons in the outer core, though far less numerous than the neutrons, exhibit their own remarkable behavior. They too form Cooper pairs, but because protons carry electric charge, their paired state is not merely a superfluid, but a superconductor. Electric currents can flow through this proton superconductor without any resistance, and magnetic fields become trapped in quantized flux tubes rather than permeating the material uniformly. The magnetic field of a neutron star, which can reach 100 million to 1 trillion Tesla at the surface, threads through the core in these discrete flux tubes, each carrying a magnetic flux of approximately 2 × 10 to the negative 15 Weber. The interaction between the neutron superfluid vortices and the proton superconductor flux tubes creates a coupling between the star's rotation and its magnetic field. As the star spins down over time, losing rotational energy to electromagnetic radiation, the vortices must migrate outward through the core. But this migration is impeded by the flux tubes, creating a complex dynamics that may explain some of the observed timing irregularities in pulsars. Below the outer core, at depths greater than 9 kilometers and densities exceeding twice the nuclear saturation density, lies the inner core. Here, the physics becomes genuinely uncertain. The pressures are so extreme that new particles may appear, hyperons containing strange quarks, or perhaps a transition to deconfined quark matter where the individual quarks are no longer bound inside neutrons and protons. Some theoretical models suggest that the inner core might contain a color superconducting phase of quark matter, where quarks pair up in ways analogous to the electron pairing in ordinary superconductors, but involving the color charge of quantum chromodynamics rather than electric charge. The central density of a neutron star may reach 5 to 10 times the density of normal nuclear matter, approximately 1 quadrillion grams per cubic centimeter. At these densities, a teaspoon of material would weigh roughly 5 billion tons. The entire mass of Mount Everest, compressed to neutron star density, would fit inside a space smaller than a grain of sand. Yet this comparison, while striking, fails to capture the true strangeness of the matter. This is not ordinary matter compressed. It is matter transformed into something fundamentally different, a quantum fluid where the distinction between individual particles becomes blurred and collective behavior dominates. The temperature profile of a neutron star also varies with depth, though not in the way one might expect. A newly formed neutron star is extraordinarily hot throughout, with core temperatures reaching 100 billion Kelvin in the first seconds after formation. But neutron stars cool rapidly through neutrino emission, and within a few hundred years, the core temperature drops to approximately 1 billion Kelvin. The surface, connected to the core through the insulating crust, cools more slowly and maintains a temperature of roughly 1 million Kelvin for thousands of years. This temperature gradient drives heat flow from the core to the surface, but the superfluid nature of the core matter affects how this heat is transported. The layered structure of a neutron star is not static, but dynamic. The crust, though solid, can crack and shift under the stresses induced by the star's rotation and magnetic field. These starquakes, as they are called, release enormous amounts of energy and may cause sudden changes in the star's rotation rate. The superfluid interior, meanwhile, can store angular momentum independently of the crust, leading to a complex interplay between the rigid outer layers and the frictionless inner fluid. Observations of neutron star cooling rates, pulse timing, and X-ray spectra provide indirect evidence for this internal structure, but many details remain uncertain. The equation of state of matter at supranuclear densities is one of the outstanding problems in nuclear physics, and neutron stars serve as natural laboratories for studying this extreme regime. Each measurement of a neutron star's mass, radius, or thermal emission constrains the possible forms that matter can take in these extraordinary objects, slowly revealing the architecture hidden beneath the pulsing surface. The numbers themselves resist intuition. At the center of a neutron star, matter reaches densities of approximately 10 to the power of 17 kilograms per cubic meter, a figure so far removed from everyday experience that it requires careful unpacking to grasp even partially. Consider that water, the substance we use as a baseline for density measurements, weighs 1,000 kilograms per cubic meter. Iron, one of the densest common materials, reaches nearly 8,000. The core of our Sun, where hydrogen fuses into helium under crushing gravitational pressure, achieves roughly 150,000 kilograms per cubic meter. Even this extreme environment pales against what exists inside a neutron star, where densities exceed solar core values by a factor of nearly 1 billion. To make this tangible, physicists often invoke a simple comparison. A teaspoon of neutron star material would weigh approximately 5 billion metric tons. This single teaspoon, if somehow transported to Earth's surface, would immediately punch through the ground, through the crust, through the mantle, and settle at the planet's core, not because of any explosive force, but simply because nothing in Earth's structure could support such concentrated mass. The gravitational pull of that teaspoon, at close range, would be measurable. It represents more mass than all the vehicles ever manufactured in human history, compressed into a volume smaller than a sugar cube. This compression arises from the complete elimination of the empty space that normally characterizes matter. In ordinary atoms, the nucleus occupies only about 1/trillionth of the atom's total volume. The rest is emptiness, populated only by the probability clouds of orbiting electrons. When gravitational collapse crushes a stellar core past the electron degeneracy threshold, this empty space vanishes. The electrons merge with protons, and the resulting neutrons pack together as tightly as the strong nuclear force permits. The matter transitions from atomic to nuclear, and the density jumps by 12 orders of magnitude. At these conditions, the concept of individual particles begins to blur. Neutrons in the outer core maintain their identity as discrete fermions, obeying the Pauli exclusion principle and generating the degeneracy pressure that supports the star. But as density increases toward the inner core, the neutrons themselves may dissolve into their constituent quarks. This hypothetical transition would produce what physicists call quark matter, a state where up and down quarks roam freely, rather than remaining bound in triplets within neutron boundaries. The existence of quark matter in neutron star cores remains unconfirmed, but theoretical models suggest it becomes energetically favorable above approximately 2 times 10 to the power of 17 kilograms per cubic meter. At these densities, the average separation between quarks shrinks below 1 femtometer, less than the diameter of a proton. The strong force, which normally confines quarks within hadrons, may weaken sufficiently through a phenomenon called asymptotic freedom to allow deconfinement. If this occurs, the inner core would consist of a quark-gluon plasma, similar in some respects to the state of the universe in the first microseconds after the Big Bang. Some theorists propose an even more exotic possibility: strange quark matter. Under sufficient pressure, the conversion of down quarks to strange quarks might become energetically favorable, producing a mixture of up, down, and strange quarks in roughly equal proportions. This strange matter, if stable, would have remarkable properties. It might represent the true ground state of matter, more stable than ordinary nuclear matter, with implications that extend far beyond neutron stars. A neutron star with a strange matter core would technically be a hybrid object, with a neutron fluid mantle surrounding a strange quark heart. The pressure required to maintain these densities defies ordinary description. At the center of a typical neutron star, pressure reaches approximately 10 to the power of 34 pascals. For comparison, the pressure at Earth's core is about 360 billion pascals, and the pressure at the Sun's center is roughly 2.5 times 10 to the power of 16 pascals. Neutron star central pressure exceeds solar core pressure by a factor of more than a quadrillion. This pressure arises from the weight of the overlying material, compressed by gravity into an ever smaller volume. Each layer presses down on the layer beneath, and the cumulative effect produces conditions unmatched anywhere else in the contemporary universe. The temperature of this compressed matter varies with the neutron star's age. A newly formed neutron star, fresh from supernova collapse, may have core temperatures exceeding 10 to the power of 11 Kelvin, hundreds of billions of degrees. At these temperatures, the matter radiates neutrinos copiously, and the star cools rapidly. Within the first 100 years, the core temperature drops to approximately 10 to the power of 9 Kelvin. After 1,000,000 years, it falls below 10 to the power of 8 Kelvin. The Crab pulsar, at roughly 1,000 years old, likely has a core temperature near 10 to the power of 8 Kelvin, still hot enough to glow in X-rays, but cooling steadily as neutrino emission continues. This cooling process itself provides information about the internal composition. Different phases of matter cool at different rates, depending on their neutrino emissivity. Quark matter, if present, would cool faster than pure neutron matter due to enhanced neutrino production through the direct Urca process. Observations of neutron star surface temperatures, combined with age estimates from supernova remnant expansion rates, allow astronomers to constrain the cooling models and thereby infer properties of the hidden interior. The equation of state, the mathematical relationship between pressure, density, and temperature, remains the central uncertainty in neutron star physics. Different theoretical models predict different maximum masses, different radius-mass relationships, and different internal compositions. The detection of gravitational waves from merging neutron stars, such as the event GW170817 observed in August 2017, provides new constraints. The way neutron stars deform under tidal forces during their final in-spiral depends on their internal stiffness, which in turn depends on the equation of state. The gravitational wave signal encodes this information, allowing physicists to extract limits on how compressible neutron star matter can be. Current observations suggest that neutron star matter is relatively stiff, meaning it resists compression more strongly than some theoretical models predicted. This stiffness supports the existence of neutron stars with masses exceeding 2 solar masses, such as PSRJ 0740 plus 6620, measured at 2.08 solar masses. A softer equation of state would cause such massive objects to collapse into black holes, but they persist as stable neutron stars, their existence constraining the physics of matter at nuclear densities. The stability of these massive neutron stars depends not only on the pressure of degenerate matter, but on another property that defines their observable behavior: rotation. A neutron star does not simply exist as a static sphere of compressed matter. It spins, and it spins with a ferocity that defies everyday experience. When a massive star collapses, it carries its angular momentum inward. The same principle that causes a figure skater to spin faster when pulling in their arms operates on a stellar scale. A star that once rotated leisurely over the course of weeks or months suddenly contracts from a radius of hundreds of thousands of kilometers to a mere 10 or 12 kilometers. The conservation of angular momentum demands that this contraction produce an enormous increase in rotational velocity. Consider the mathematics. Angular momentum equals the moment of inertia multiplied by angular velocity. When the radius decreases by a factor of 10,000, the moment of inertia, which depends on the square of the radius, decreases by a factor of 100 million. To conserve angular momentum, the angular velocity must increase by that same factor. A star that completed one rotation per month before collapse might spin hundreds of times per second afterward. The fastest spinning neutron star currently known is PSRJ 1748-2446 AD, located in the globular cluster Terzan 5, approximately 18,000 light-years from Earth. This object completes 716 rotations every second. Its equatorial surface moves at roughly 24% of the speed of light, approximately 70,000 kilometers per second. At this velocity, the star's equator bulges outward, distorting the neutron star from a perfect sphere into an oblate spheroid. The centrifugal force at the surface nearly rivals the gravitational force attempting to hold the star together. Such extreme rotation rates do not arise from collapse alone. The initial spin period of a newborn neutron star typically ranges from tens to hundreds of milliseconds. The Crab pulsar, born in the supernova of 1054 CE, currently rotates once every 33.5 milliseconds, having slowed from its initial period over nearly 1,000 years. To achieve rotation rates exceeding 100 rotations per second requires an additional mechanism: accretion from a binary companion. When a neutron star exists in a binary system with a normal star, matter can flow from the companion onto the neutron star's surface. This matter does not fall directly inward. Instead, it spirals in through an accretion disk, carrying angular momentum with it. As the neutron star accumulates mass, it also accumulates spin. Over hundreds of millions of years, this process can accelerate a neutron star from a sedate rotation period of several seconds to the millisecond regime. These recycled pulsars, as astronomers call them, represent some of the most precise natural clocks in the universe. PSRB 1937+21, discovered in 1982, rotates 641 times per second, with a stability that rivals atomic clocks. Its period of 1.5578 milliseconds remains constant to better than 1 part in 10 to the power of 15 over timescales of years. This precision makes millisecond pulsars invaluable tools for detecting gravitational waves through pulsar timing arrays, where tiny variations in pulse arrival times reveal the passage of space-time ripples from distant cosmic events. But rotation alone does not make a pulsar observable. The defining characteristic of a pulsar is its magnetic field, and the interaction between rapid rotation and intense magnetism produces the lighthouse beam that sweeps across the cosmos. Neutron stars possess magnetic fields of staggering strength. A typical pulsar carries a surface magnetic field of approximately 10 to the 8th power Tesla, roughly 1 trillion times stronger than Earth's magnetic field, and 100 million times stronger than the most powerful magnets humans have constructed. This field does not arise from the same mechanisms that generate planetary magnetic fields. Instead, it represents the compressed remnant of the progenitor star's original magnetic field, amplified by the same factor that amplifies the rotation rate during collapse. The magnetic field of a neutron star does not align perfectly with its rotation axis. In most pulsars, the magnetic axis tilts at an angle to the spin axis, ranging from a few degrees to nearly 90 degrees. This misalignment proves crucial for pulsar emission. As the neutron star rotates, its magnetic poles sweep through space like the beams of a lighthouse, and if Earth happens to lie along the path of one of these beams, we detect a pulse of radiation with each rotation. The emission mechanism involves the acceleration of charged particles along the magnetic field lines near the neutron star's poles. The rotating magnetic field induces enormous electric fields at the stellar surface, fields strong enough to rip electrons and positrons from the iron crust and accelerate them to relativistic velocities. These particles stream outward along the curved magnetic field lines, emitting radiation as they accelerate. The physics of this emission involves a process called curvature radiation. When a charged particle follows a curved path, it emits electromagnetic radiation in a narrow beam pointed along its direction of motion. Near the magnetic poles of a pulsar, particles follow the curved magnetic field lines, emitting radiation that combines into a coherent beam. The frequency of this radiation depends on the curvature of the field lines and the energy of the particles, producing emission across the electromagnetic spectrum from radio waves to gamma rays. The region where this emission occurs is called the magnetosphere, a zone dominated by the neutron star's magnetic field extending outward to the light cylinder, the distance at which the co-rotating magnetic field would have to move at the speed of light. For a pulsar with a rotation period of 33 milliseconds, like the Crab pulsar, the light cylinder lies approximately 1,600 kilometers from the stellar center. Beyond this distance, the magnetic field lines cannot remain closed, and they open outward, allowing particles and energy to escape into space. The energy powering pulsar emission comes from the neutron star's rotation. As the magnetic field sweeps through space, it radiates electromagnetic energy, and this radiation carries away angular momentum. The pulsar gradually slows down, its rotation period increasing by tiny increments over time. The Crab pulsar's period increases by approximately 36.4 nanoseconds per day, corresponding to a spin-down luminosity of about 4.6 times 10 to the power of 31 watts, roughly 100,000 times the total energy output of the Sun, radiated primarily as a relativistic wind of particles and magnetic fields rather than visible light. This spin-down rate provides a direct measurement of the pulsar's magnetic field strength. The relationship between period derivative, and magnetic field follows from the physics of magnetic dipoles radiation. For the Crab pulsar, the inferred surface magnetic field is approximately 3.8 times 10 to the power of 8 Tesla. For slower, older pulsars with longer periods and smaller spin-down rates, the magnetic fields are typically weaker, in the range of 10 to the power of 4 to 10 to the power of 6 Tesla. The pulse profile, the shape of the detected signal as a function of rotational phase, carries information about the geometry of the emission region. Some pulses show a single sharp peak, indicating that only one magnetic pole sweeps across our line of sight. Others display 2 peaks separated by half a rotation period, revealing emission from both poles. The width of each peak, typically a few % of the rotation period, reflects the angular size of the emission beam. At radio wavelengths, pulsar emission exhibits remarkable properties. Individual pulses vary dramatically in intensity and shape, sometimes disappearing entirely for several rotations before returning. Yet when thousands of pulses are averaged together, the resulting profile remains extraordinarily stable, maintaining its shape over decades of observation. This stability indicates that while the emission process involves chaotic, turbulent plasma physics on short timescales, the underlying geometry of the magnetosphere remains fixed. The radio emission itself is coherent, meaning that particles radiate in phase with one another, producing intensities far greater than the sum of individual particle emissions. The brightness temperature of pulsar radio emission can exceed 10 to the power of 25 Kelvin, a number that has no meaning as an actual temperature, but indicates the extraordinary coherence of the emission process. No thermal source could produce such intense, narrowly beamed radiation. The mechanism behind this coherent emission remains one of the most challenging problems in astrophysics, a puzzle that has persisted for more than 50 years since Jocelyn Bell Burnell first noticed the regular pulses arriving from what would be named PSRB 1919+21. The basic geometry is well understood. A rotating neutron star with a magnetic axis tilted relative to its rotation axis sweeps beams of radiation across space like a lighthouse beam sweeping across a dark ocean. But the physics that generates those beams, the precise processes that convert rotational energy into coherent radio waves, continues to resist complete explanation. Consider the geometry more carefully. A neutron star with a radius of approximately 12 kilometers rotates about an axis. Its magnetic field, with a strength that can reach 10 to the 8th power Tesla at the surface, does not align with this rotation axis. The angle between them, called the obliquity angle, varies from pulsar to pulsar and determines the observed pulse shape. When the magnetic pole points toward Earth, the observer detects a pulse. When it points away, the signal fades. The period between pulses equals the rotation period of the star, which for the original pulsar discovered in 1967 is 1.337 seconds, a value so stable that early observers briefly wondered if they had detected an artificial signal from an extraterrestrial civilization. The magnetic field of a neutron star does not exist in isolation. It threads through the surrounding space, but that space is not empty. The intense electric fields generated by the rotating magnetic field, fields that can reach 10 to the power of 12 volts per meter near the stellar surface, rip electrons and positrons from the neutron star's crust and accelerate them to relativistic velocities. These particles cannot cross magnetic field lines easily. Instead, they flow along them, populating a region called the magnetosphere that extends outward from the star. The magnetosphere has structure. Close to the neutron star, within a region called the closed magnetosphere, magnetic field lines loop back to the stellar surface. Particles trapped on these field lines remain bound to the star, flowing back and forth along closed path. But beyond a certain distance, the field lines no longer close. They extend outward into space, eventually connecting to the interstellar medium. The boundary between closed and open field lines defines the polar cap, a small region near each magnetic pole where particles can escape the star's gravitational and magnetic grip. The polar cap of a typical pulsar has a radius of only a few hundred meters, perhaps 500 meters for a pulsar with a 1-second period. This tiny region, covering less than 1/1,000,000th of the neutron star's surface area, serves as the source of all the radio emission that makes the pulsar detectable across thousands of light years. The energy density within this region is extraordinary. Electric fields accelerate particles to Lorentz factors of 10 to the 6th power or higher, meaning the particles travel at 99.9999% the speed of light. Their effective mass increased 1,000,000-fold by relativistic effects. As these ultra-relativistic electrons and positrons stream outward along the open magnetic field lines, they encounter conditions that force them to radiate. The magnetic field curves, and particles following curved field lines must accelerate, not in speed, but in direction. This acceleration produces radiation through a process called curvature radiation, analogous to synchrotron radiation, but following the curvature of the magnetic field rather than gyrating around it. A single electron following a field line with a radius of curvature of 10 to the 7th meters while traveling at nearly the speed of light emits gamma-ray photons with energies of millions of electron volts. These gamma rays do not escape directly. The magnetic field is too strong. When a gamma-ray photon travels through a region where the magnetic field exceeds approximately 4.4 times 10 to the power of 9 Tesla, the quantum critical field strength, it can spontaneously convert into an electron-positron pair. This process, called magnetic pair production, requires no interaction with matter. The magnetic field itself provides the necessary conditions for the photon to materialize into particles. The threshold depends on the angle between the photon's direction and the magnetic field. But near the polar cap of a typical pulsar, the conditions are met routinely. The newly created electron-positron pairs find themselves in the same intense magnetic field that created them. They too accelerate along field lines, emit curvature radiation, produce more gamma rays, which create more pairs, which radiate more gamma rays. This cascade process, called a pair cascade, multiplies the number of particles exponentially. A single primary electron extracted from the neutron star surface can generate 10 to the power of 4 to 10 to the power of 5 secondary pairs through this cascade mechanism. The magnetosphere fills with plasma, not because particles drift in from outside, but because the pulsar manufactures them from pure electromagnetic energy. This pair plasma, streaming outward along open field lines at relativistic velocities, carries the energy that eventually becomes radio emission. But the conversion process remains incompletely understood. The radio waves themselves originate at altitudes of a few hundred to a few thousand kilometers above the neutron star surface, far above the polar cap where the pairs are created, but still deep within the magnetosphere. At these heights, the plasma density and the magnetic field strength create conditions where collective plasma instabilities can develop. The coherence of pulsar radio emission, the fact that particles radiate in phase rather than independently, requires some mechanism to organize their motion. One leading theory involves plasma instabilities that create bunches of particles, clumps containing perhaps 10 to the power of 20 electrons and positrons moving together as a unit. When such a bunch accelerates, all its particles radiate in phase, producing emission whose intensity scales as the square of the number of particles rather than linearly. This explains how pulsars can achieve brightness temperatures of 10 to the power of 25 to 10 to the power of 30 Kelvin, values that would be impossible for incoherent thermal emission. The specific instability responsible for this bunching remains debated. Candidates include the two-stream instability, where faster and slower particle populations interact to create density waves, and various forms of Mars emission, where population inversions in the energy levels of the plasma lead to stimulated emission of radiation. The plasma physics involved operates in a regime, ultra-relativistic velocities, ultra-strong magnetic fields, pair-dominated composition, that has no laboratory analog. Theorists must work from first principles, and the mathematics quickly becomes intractable. Observations provide constraints. The Crab pulsar, with its 33 millisecond period, emits giant pulses that can be thousands of times brighter than average pulses, lasting for only microseconds or even nanoseconds. These giant pulses demonstrate that the emission mechanism can concentrate energy into extremely short bursts, implying coherent emission from very compact regions. The Vela pulsar, spinning at 89 milliseconds per rotation, shows microstructure within its pulses on timescales of microseconds, corresponding to emission regions only a few hundred meters across. The polarization of pulsar radio emission offers additional clues. Pulsar signals are typically highly polarized, with both linear and circular polarization components that vary systematically across the pulse profile. The position angle of linear polarization often swings smoothly through the pulse, following a pattern predicted by the rotating vector model, a geometric consequence of viewing a rotating magnetic dipole from a fixed direction. This agreement confirms the basic lighthouse geometry, while the deviations from the simple model reveal the complexity of the emission region. Some pulses exhibit mode changing, abruptly switching between two or more distinct pulse profiles that persist for minutes to hours before switching back. Others show nulling, periods when the radio emission ceases entirely for tens to thousands of rotation periods before resuming. These phenomena indicate that the emission mechanism, while stable on average, can undergo dramatic state changes. The magnetosphere appears to have multiple quasi-stable configurations, and transitions between them alter the observable properties of the pulsar. The energy budget of pulsar emission is remarkably inefficient. A typical pulsar converts only about 10 to the power of -6 of its rotational energy loss into radio waves. The rest goes into the pulsar wind. a relativistic outflow of particles and magnetic field that inflates a bubble called a pulsar wind nebula. The Crab Nebula, visible in optical telescopes as a ghostly blue glow surrounding the pulsar, represents the accumulated energy of nearly 1,000 years of pulsar wind, shocked and radiating as it collides with the slower-moving supernova remnant. Among the population of neutron stars scattered throughout the galaxy, a small fraction possess magnetic fields so intense that they defy ordinary description. These objects, known as magnetars, represent the most powerfully magnetized entities in the known universe, with surface fields reaching and exceeding 10 to the power of 11 Tesla, a value roughly a quadrillion times stronger than Earth's modest magnetic field of 50 microtesla. To place this in perspective, the strongest sustained magnetic fields produced in terrestrial laboratories reach approximately 45 Tesla. Medical MRI machines operate at fields of 1.5 to 3 Tesla. The magnetic field at the surface of a typical pulsar, already extraordinary by human standards, measures around 10 to the power of 8 Tesla. A magnetar surpasses even this by factors of 1,000 or more, entering a regime where the magnetic field itself begins to alter the fundamental properties of matter and light. The origin of these extreme fields remains an area of active research, but the leading hypothesis involves a dynamo mechanism operating during the first seconds of a neutron star's existence. When the core of a massive star collapses, the resulting proto-neutron star is hot, turbulent, and convective. If this convection is vigorous enough, and if the star is rotating rapidly enough, with periods of a few milliseconds, the combination of differential rotation and convective motion can amplify any seed magnetic field exponentially. This process, analogous to the dynamo that generates Earth's magnetic field, but operating under far more extreme conditions, can boost the field strength by many orders of magnitude within the brief window before the neutron star cools and solidifies. The critical factor appears to be the initial rotation rate. Simulations suggest that proto-neutron stars with rotation periods shorter than about 3 milliseconds can sustain the vigorous convection necessary for magnetar strength field generation. Slower rotators produce ordinary pulses. This sensitivity to initial conditions explains why magnetars are rare. Perhaps only 1 in 10 neutron stars is born spinning fast enough to become a magnetar. Once established, the magnetic field of a magnetar is not static. It is anchored in the neutron star's crust, a crystalline lattice of neutron-rich nuclei, and threads through the superfluid interior. The field exerts tremendous stresses on this structure. At 10 to the power of 11 Tesla, the magnetic pressure exceeds 4 times 10 to the power of 25 pascals, comparable to the pressure at the base of the crust itself. This creates an inherently unstable situation. The crust, though extraordinarily strong by terrestrial standards, cannot indefinitely resist the magnetic forces attempting to reconfigure the field into a lower energy state. The result is a phenomenon unique to magnetars: the starquake. When accumulated magnetic stress exceeds the yield strength of the crust, the surface fractures and shifts. These events release enormous quantities of energy in fractions of a second. On December 27, 2004, a magnetar designated SGR 1806-20 located approximately 50,000 light-years away in the constellation Sagittarius, produced a giant flare that briefly outshone the entire galaxy in gamma rays. The initial spike lasted only 0.2 seconds, but released approximately 10 to the power of 39 joules of energy, more than the Sun emits in 150,000 years. The gamma-ray flux at Earth, despite the vast distance, was sufficient to ionize the upper atmosphere and disturb radio communications on the planet's night side. This event, the most energetic outburst ever observed from within the Milky Way, provided direct evidence of the processes occurring in magnetar crusts. The energy release is understood as the sudden reconfiguration of the magnetic field following a crustal fracture, analogous to an earthquake, but powered by magnetic rather than tectonic stress. The flare's oscillating tail, which persisted for several minutes, showed periodic variations at frequencies of 18, 26, 30, 92, 150, 625, and 1,840 Hz. These frequencies correspond to seismic oscillations of the neutron star itself, the entire object ringing like a struck bell, with different modes corresponding to different patterns of crustal vibration. The detection of these quasi-periodic oscillations opened a new field of asteroseismology applied to neutron stars. Each oscillation frequency encodes information about the star's internal structure, the thickness and composition of the crust, the properties of the superfluid core, the geometry of the magnetic field. The 625 Hz oscillation, for instance, is consistent with a fundamental toroidal mode of the crust, while the 18 Hz signal may represent a global oscillation involving the entire stellar interior. By analyzing these frequencies, researchers can probe the equation of state of matter at nuclear densities, physics that cannot be replicated in any laboratory. Magnetars also emit persistent X-rays at luminosities far exceeding what their rotation can supply. A typical magnetar radiates 10 to the power of 28 to 10 to the power of 29 watts in X-rays, yet its rotational energy loss, calculated from its spin-down rate, amounts to only 10 to the power of 26 watts or less. The excess energy must come from another source, the decay of the magnetic field itself. As the field slowly dissipates, its energy is converted into heat within the neutron star's crust and magnetosphere. This process, known as magnetic field decay, operates on timescales of thousands to tens of thousands of years, explaining why magnetars are observed as young objects associated with recent supernova remnants. The magnetic field of a magnetar also creates exotic effects on the quantum vacuum. In fields exceeding approximately 4.4 times 10 to the power of 9 Tesla, a threshold known as the quantum critical field or Schwinger limit, the vacuum itself becomes birefringent. Light traveling through such a field experiences different refractive indices depending on its polarization relative to the field direction. This phenomenon, predicted by quantum electrodynamics but never observed in laboratory settings, has been detected in observations of magnetar thermal emission. The polarization properties of X-rays from the magnetar are XJ 185.6.5-3754 show signatures consistent with vacuum birefringence, providing a direct test of quantum electrodynamics in the strong field regime. At even higher field strengths, approaching 10 to the power of 13 Tesla. Atoms themselves are distorted beyond recognition. The magnetic force on electrons exceeds the Coulomb attraction to the nucleus, causing atoms to elongate into needle-like structures aligned with the field. Hydrogen atoms, normally spherical with a radius of about 0.05 nanometers, become cigar-shaped objects hundreds of times longer than they are wide. The binding energy of these magnetically distorted atoms increases dramatically, and the chemistry of matter in such fields bears no resemblance to ordinary experience. The population of known magnetars numbers only about 30 objects, identified through their characteristic X-ray emission and occasional bursting activity. They are classified into two observational categories: soft gamma repeaters, which produce repeated bursts of gamma rays, and anomalous X-ray pulsars, which show persistent X-ray emission with unusual spectral properties. These categories are now understood to represent different manifestations of the same underlying phenomenon: neutron stars with magnetar strength fields observed at different stages of activity or from different viewing angles. The rotation periods of magnetars cluster between 2 and 12 seconds, far slower than ordinary pulsars. This slow rotation is a consequence of their intense magnetic fields, which break the star's spin with exceptional efficiency. A magnetar born rotating at millisecond periods would spin down to periods of several seconds within a few thousand years. The spin-down rate itself provides a method for estimating the surface field strength. Magnetar SGR 1900 plus 14, for example, shows a period derivative of 6 times 10 to the power of minus 11 seconds per second, implying a dipole field of approximately 7 times 10 to the power of 10 Tesla. The magnetosphere surrounding a magnetar differs qualitatively from that of an ordinary pulsar. The magnetic field is strong enough to suppress the pair creation cascades that power pulsar radio emission, which explains why most magnetars are radio quiet. Instead, the magnetosphere is filled with a dense plasma of electrons and positrons, heated to temperatures exceeding 10 to the power of 9 Kelvin by magnetic reconnection events and crustal heating. This plasma radiates thermally in X-rays, producing the persistent emission that characterizes magnetar observations. Yet beneath this magnetically dominated exterior, the solid crust of a neutron star experiences stresses that build over years, decades, or centuries until the material can no longer hold its shape. The result is a starquake, a sudden fracture in the crystalline lattice that releases energy in a fraction of a second and leaves measurable signatures in the star's rotation. These events, detected as glitches in pulsar timing, provide one of the few direct windows into the internal structure of neutron stars, revealing the complex interplay between the rigid crust and the superfluid interior. The crust of a neutron star, though only about 1 kilometer thick, contains matter under extraordinary strain. The crystalline lattice of iron group nuclei, arranged in a body-centered cubic structure, must support the weight of overlying material in a gravitational field 200 billion times stronger than Earth's. As the star spins down due to magnetic braking, losing rotational energy at a rate determined by its magnetic field strength and rotation period, the equilibrium shape of the crust must change. A rapidly rotating neutron star is oblate, bulging at the equator due to centrifugal forces. As the rotation slows, the star attempts to become more spherical, but the rigid crust resists this deformation. Stress accumulates in the lattice, stored as elastic energy, until the material reaches its breaking point. The Vela pulsar, designated PSRB0833-45, has provided some of the most detailed observations of glitch behavior since its discovery in 1968. Located approximately 950 light-years from Earth in the constellation Vela, this young pulsar rotates with a period of 89 milliseconds and has exhibited more than 20 large glitches over the past 5 decades. The typical Vela glitch involves a sudden increase in rotation frequency of about 10 to the power of -6 Hz, a fractional change of roughly 10 parts per million. In absolute terms, this means the star's rotation period decreases by approximately 100 nanoseconds in less than a minute. The angular momentum required for this spin-up, if it came from the crust alone, would require the entire outer layer to suddenly contract by about 1 centimeter. But the crust cannot provide this angular momentum. The explanation lies in the superfluid neutrons that permeate the inner crust and extend into the stellar core. These neutrons, freed from the nuclei in the neutron drip layer at densities above 4 × 10 to the 11th power kilograms per cubic meter, form Cooper pairs and flow without friction. Unlike the solid crust, which is locked to the magnetic field and slows down as the star loses rotational energy, the superfluid component can maintain its rotation independently. Over time, a velocity difference develops between the crust and the superfluid interior, with the superfluid spinning faster than the observable surface. The superfluid rotation is not uniform, but quantized into discrete vortices, each carrying a single quantum of angular momentum equal to h over 2mn, where h is Planck's constant and mn is the neutron mass. In a neutron star rotating at 11 times per second, like the Vela pulsar, the superfluid contains approximately 10 to the power of 19 vortices, each separated by about 0.01 millimeters. These vortices tend to pin to the nuclei in the crustal lattice, held in place by the strong nuclear force. As the crust slows down, the pinned vortices resist moving outward, and the velocity lag between the superfluid and the crust increases. The system stores angular momentum like a wound spring. When the stress exceeds a critical threshold, the vortices unpin catastrophically. Billions of vortices suddenly migrate outward through the crust, transferring their excess angular momentum to the observable surface. The crust spins up, the superfluid spins down, and the system reaches a new equilibrium. This vortex avalanche occurs on timescales shorter than current observational resolution, less than 40 seconds for most observed glitches, and possibly as fast as a few seconds. The Vela pulsar's glitches release approximately 10 to the power of 36 joules of rotational energy, equivalent to the total energy output of the Sun over several weeks, all transferred in moments. The Crab pulsar presents a contrasting case. Its glitches are smaller, typically involving fractional frequency changes of 10 to the power of -8 to 10 to the power of -9, about 100 times weaker than Vela's events. The Crab also shows a different recovery pattern. After a glitch, the rotation frequency partially returns toward its pre-glitch value over days to weeks, suggesting that only a fraction of the transferred angular momentum remains permanently coupled to the crust. This recovery behavior indicates that the superfluid in the crab pulsar's interior responds differently, perhaps because the star's higher temperature, it is only about 1,000 years old compared to Vela's 11,000 years, affects the pinning strength of vortices to crustal nuclei. The relationship between starquakes and glitches remains a subject of active research. Some glitches may be triggered by actual fractures in the crust, sudden breaking of the crystalline lattice that releases the pinned vortices. The energy released in such a fracture would be enormous by terrestrial standards. A starquake releasing 10 to the power of -10 of the star's gravitational binding energy would liberate approximately 10 to the power of 36 joules, comparable to the rotational energy change observed in large glitches. The fractured crust would then resettle into a new configuration, slightly more spherical than before, with the stress temporarily relieved until the continued spin-down rebuilds it. Magnetars experience particularly violent crustal activity. The decay of their ultra-strong magnetic fields induces currents in the crust that heat the material and create additional stresses beyond those from spin-down. Magnetar SGR-1806-20 produced a giant flare on December 27, 2004 that released approximately 2 × 10 to the power of 39 joules in less than 0.2 seconds, more energy than the Sun emits in 250,000 years. This event was likely triggered by a catastrophic rearrangement of the magnetic field, accompanied by massive crustal fracturing. The X-ray light curve showed quasi-periodic oscillations at frequencies of 18, 26, 30, 92, 150, 625, and 1840 Hz, interpreted as seismic vibrations of the neutron star crust ringing like a struck bell. These oscillation frequencies encode information about the star's internal structure. The lowest frequency modes, around 18 to 30 Hz, correspond to global shear oscillations of the crust, while higher frequencies represent overtones and toroidal modes. By comparing observed frequencies to theoretical models, researchers can constrain the thickness of the crust, the shear modulus of the crystalline lattice, and even the properties of matter at nuclear density. The 625 Hz oscillation from SGR-1806-20 suggests a crustal shear speed of approximately 10 to the 8th power meters per second, consistent with a lattice of iron group nuclei under the extreme pressures found at depths of several hundred meters. The glitch activity of a pulsar correlates with its characteristic age, defined as the ratio of period to twice the period derivative. Young pulsars like Vela and the Crab glitch frequently, while older pulsars with characteristic ages exceeding 1 million years rarely show detectable events. This pattern suggests that glitch behavior evolves as the star cools and its superfluid properties change. The critical temperature for neutron superfluidity in the inner crust is approximately 10 to the power of 9 to 10 to the power of 10 Kelvin, and as a neutron star cools below this threshold over thousands of years, the superfluid fraction increases and the pinning dynamics shift. The post-glitch recovery reveals multiple timescales in the coupling between different components of the star. Immediately after a glitch, the crust and the charged particles in the core are tightly coupled by the magnetic field, responding together on time scales of seconds. The superfluid in the inner crust recouples over days to weeks, as vortices repin to the lattice and the velocity lag rebuilds. The superfluid in the core, if it exists, may couple on even longer time scales of months to years, though this component is more difficult to identify observationally. Each timescale provides constraints on the viscosity, pinning strength, and mutual friction between the superfluid and normal components. The internal dynamics of isolated neutron stars, with their glitches and gradual recoveries, reveal the complex interplay of superfluids and crystalline matter within a single compact object. But neutron stars rarely exist in true isolation. Approximately half of all massive stars form in binary systems, gravitationally bound to a companion from birth. When one of these stars collapses into a neutron star, the binary often survives the supernova explosion, leaving the compact remnant in orbit with its companion. These binary neutron star systems, and the related systems where a neutron star orbits an ordinary star, provide some of the most precise laboratories for studying gravity, mass transfer, and the ultimate fate of degenerate matter. The geometry of a binary system is governed by the gravitational potential of both stars, which together create a complex landscape through which matter flows. The French mathematician Édouard Roche first described this potential in the 19th century, calculating the surfaces of equal gravitational and centrifugal potential around two orbiting bodies. The most important of these surfaces is the Roche lobe, the teardrop-shaped region around each star within which material is gravitationally bound to that star alone. The two Roche lobes meet at a single point between the stars, called the inner Lagrangian point, or L1, where the gravitational pull of both stars and the centrifugal force of the orbital motion precisely balance. In a typical binary system, the two stars begin their lives well within their respective Roche lobes, separated by millions or billions of kilometers. But stars evolve. As a star exhausts the hydrogen in its core and begins burning heavier elements, it expands dramatically, sometimes increasing its radius by a factor of 100 or more. A star that was once comfortably contained within its Roche lobe may swell until its outer atmosphere reaches the L1 point. At this moment, matter begins to flow from the expanding star onto its companion, a process called Roche lobe overflow. The physics of this mass transfer depends critically on the mass ratio of the two stars and the evolutionary state of the donor. When the donor star is more massive than the accretor, mass transfer tends to be unstable. As matter flows from the donor to the accretor, the donor's Roche lobe shrinks, while the star itself may continue to expand, accelerating the mass transfer in a runaway process. This unstable transfer can lead to common envelope evolution, where the compact object spirals into the outer layers of its companion, dramatically shrinking the orbital separation through friction. Many of the closest binary neutron star systems observed today, with orbital periods of just hours, likely passed through such a common envelope phase earlier in their evolution. When the donor is less massive than the accretor, mass transfer proceeds more gently. The donor's Roche lobe expands as it loses mass, and the system can achieve a stable configuration where the mass transfer rate is set by the evolutionary expansion of the donor star. In systems containing a neutron star and a low-mass companion, this stable mass transfer can persist for billions of years, with matter trickling onto the neutron star at rates of 10 to the power of -10 to 10 to the power of -8 solar masses per year. The matter that crosses the L1 point does not fall directly onto the neutron star. Conservation of angular momentum prevents this. Instead, the transferred material carries the orbital angular momentum of the donor star's outer layers, which is substantial. This angular momentum forces the infalling matter into orbit around the neutron star, forming an accretion disk. The disk extends from near the neutron star's surface out to a radius determined by the specific angular momentum of the transferred material, typically tens of thousands of kilometers. Within the accretion disk, matter follows nearly circular Keplerian orbits, with the orbital velocity increasing toward the center according to the familiar relation phi equals the square root of gm/r. At the inner edge of a disk around a 1.4 solar mass neutron star, matter orbits at velocities approaching 100,000 kilometers per second, roughly 1/3 the speed of light. The differential rotation between adjacent annuli of the disk creates shear, and this shear, combined with turbulent viscosity, causes angular momentum to be transported outward through the disk, while matter spirals slowly inward. The source of this turbulent viscosity remained mysterious for decades. Simple molecular viscosity is far too weak to explain the observed accretion rates. The solution came in 1991, when Stephen Balbus and John Hawley demonstrated that a weak magnetic field threading a differentially rotating disk is unstable to the magnetorotational instability, or MRI. This instability amplifies small perturbations in the magnetic field, generating turbulence that efficiently transports angular momentum outward. The MRI operates whenever the angular velocity decreases outward, which is precisely the condition in a Keplerian disk. As matter spirals inward through the disk, gravitational potential energy is converted into heat through viscous dissipation. Half of this energy goes into increasing the orbital kinetic energy of the infalling matter, while the other half is radiated away as thermal emission. The temperature of the disk increases toward the center, following a profile where T scales as e to the -3/4 power. At the inner edge of a disk around an accreting neutron star, temperatures reach tens of millions of Kelvin, hot enough to emit primarily in X-rays. The total luminosity of an accretion disk depends on the mass accretion rate and the depth of the gravitational potential well. For a neutron star with a radius of 10 kilometers, matter falling from infinity releases approximately 200 megaelectron volts per nucleon, compared to just 26 megaelectron volts per nucleon from hydrogen fusion. Accretion onto a neutron star is therefore nearly 8 times more efficient at converting mass to energy than nuclear fusion. At accretion rates of 10 to the power of -8 solar masses per year, the resulting luminosity approaches 10 to the power of 38 watts, comparable to the Eddington luminosity at which radiation pressure balances gravity. The inner edge of the accretion disk does not extend all the way to the neutron star's surface in most systems. The neutron star's magnetic field, even if relatively weak by magnetar standards, is strong enough to disrupt the disk at a characteristic radius called the magnetospheric radius or Alfvén radius. At this distance, the magnetic pressure of the neutron star's dipole field equals the ram pressure of the infalling material. For a neutron star with a surface field of 10 to the power of 8 Tesla, accreting at 10 to the power of -9 solar masses per year, the magnetospheric radius is approximately 100 kilometers, 10 times the stellar radius. Inside the magnetospheric radius, matter is forced to follow the magnetic field lines rather than continuing in Keplerian orbits. The field channels the accreting plasma toward the magnetic poles, where it crashes onto the neutron star's surface at velocities of roughly 0.3 to 0.5 times the speed of light. The kinetic energy of this infalling matter is converted to thermal energy in a shock just above the surface, creating hot spots at the magnetic poles with temperatures exceeding 10 to the power of 8 Kelvin. These hot spots emit X-rays, and as the neutron star rotates, the hot spots sweep in and out of view, producing periodic pulsations in the X-ray flux. The angular momentum carried by the accreting matter has profound effects on the neutron star's rotation. Each gram of material that reaches the stellar surface deposits angular momentum, spinning up the neutron star over time. The equilibrium spin period, where the magnetospheric radius equals the corotation radius at which the disk would rotate at the same rate as the star, depends on the magnetic field strength and accretion rate. For typical parameters, this equilibrium period lies in the range of milliseconds to seconds. The fastest spinning neutron stars, the millisecond pulsars rotating hundreds of times per second, are thought to be the end products of this spin-up process. These objects, sometimes called recycled pulsars, were once slowly rotating neutron stars that accreted matter from a companion over billions of years, gradually increasing their spin rate until the companion was exhausted or the binary was disrupted. The current record holder, PSRJ 1748-2446 AD, rotates at 716 times per second, with its equator moving at roughly 24% of the speed of light. Binary systems containing 2 neutron stars represent the final stage of evolution for some massive binary stars. Both components have completed their lives, exploded as supernovae, and left behind compact remnants still gravitationally bound to each other. These double neutron star systems are extraordinarily rare, with only about 20 confirmed examples known in the Milky Way. The most famous, PSRB 1913+16, was discovered by Russell Hulse and Joseph Taylor in 1974 and provided the first indirect evidence for gravitational waves. The orbital dynamics of double neutron star systems are exquisitely clean, governed almost entirely by gravity with minimal complications from mass transfer or tidal effects. The 2 point-like masses trace out elliptical orbits that precess slowly due to general relativistic effects. For PSRB 1913+16, the periastron advances by 4.2 degrees per year, more than 35,000 times faster than the relativistic precession of Mercury's orbit around the Sun. This precession, combined with other relativistic effects like gravitational redshift and Shapiro delay, allows the masses of both neutron stars to be measured with extraordinary precision, 1.438 and 1.390 solar masses, with uncertainties of less than 0.001 solar masses. Most remarkably, the orbital period of PSRB 1913 plus 16 is decreasing by 76.5 microseconds per year, exactly as predicted by general relativity for a system losing energy to gravitational wave emission. The two neutron stars, each roughly 20 kilometers across, orbit their common center of mass every 7.75 hours at a separation of about 2 million kilometers. As they orbit, they stir the fabric of space-time, generating ripples that carry energy away from the system at a rate of about 7.35 times 10 to the power of 24 watts. This energy loss causes the orbit to shrink and the orbital period to decrease, a decay that has been tracked for nearly 50 years and matches the predictions of general relativity to within 0.2%. The gravitational wave emission that slowly drains energy from binary neutron star systems will eventually bring the two stars together. For PSRB 1913 plus 16, this final merger will occur in approximately 300 million years. As the orbit shrinks, the gravitational wave frequency increases, sweeping upward through the sensitive band of ground-based detectors like LIGO and Virgo in the final minutes before coalescence. The first direct detection of gravitational waves from a binary neutron-star merger came on August 17, 2017, when the event designated QW170817 was observed by both LIGO detectors and the Virgo detector in Italy. The gravitational wave signal from GW170817 lasted approximately 100 seconds in the detector's sensitive band, beginning at a frequency of about 24 Hz and chirping upward to nearly 500 Hz before the signal ended. The waveform encoded the masses of the two neutron stars, measured to be between 1.17 and 1.60 solar masses each, with a total mass of 2.74 solar masses. The signal also constrained the tidal deformability of the neutron stars, a parameter that depends on the equation of state of ultradense matter, and thus provides information about the physics of neutron star interiors. Unlike binary black hole mergers, which produce only gravitational waves, the merger of two neutron stars releases a spectacular electromagnetic counterpart. Within 2 seconds of the gravitational wave signal, the Fermi Gamma Ray Space Telescope detected a short gamma-ray burst from the same location, confirming decades of theoretical speculation that short gamma-ray bursts originate from neutron star mergers. Over the following days and weeks, telescopes across the electromagnetic spectrum observed the afterglow of the merger, including a distinctive optical and infrared transient called a kilonova. The kilonova emission arises from the radioactive decay of heavy elements synthesized in the neutron-rich debris ejected during and after the merger. The rapid neutron capture process, or R process, builds elements heavier than iron by bombarding seed nuclei with neutrons faster than the nuclei can decay. This process requires an environment with an extremely high neutron density, conditions that are difficult to achieve in ordinary stellar environments, but are naturally present in the material flung outward during a neutron star merger. The observed kilonova from GW 170817 confirmed that such mergers are a major, perhaps dominant, source of R process elements in the universe, including precious metals like gold and platinum. The synthesis of heavy elements in neutron star mergers represents just one manifestation of the extraordinary physics that unfolds when compact objects interact with companion stars. Across the galaxy, thousands of binary systems exist where a neutron star or black hole draws material from a stellar partner, creating some of the most luminous X-ray sources in the sky and providing natural laboratories for studying matter under conditions impossible to replicate on Earth. When a neutron star or black hole orbits close enough to a normal star, gravitational forces can strip material from the companion's outer layers. This process depends critically on the geometry of the system, specifically on the shape of the gravitational potential created by the two orbiting masses. The French mathematician Édouard Roche calculated in the 19th century that each star in a binary system possesses a teardrop-shaped region of gravitational influence. When a star expands to fill this region, material at the point where the two teardrops meet experiences equal gravitational pull from both objects. At this Lagrangian point, matter can flow from one star to the other, initiating the process of mass transfer that powers X-ray binaries. The transferred material does not fall directly onto the compact object. Conservation of angular momentum forces the gas to spiral inward, forming a flattened disk of material rotating around the neutron star or black hole. This accretion disk becomes the engine that converts gravitational potential energy into the intense radiation that makes these systems visible across cosmic distances. A typical accretion disk around a neutron star might extend from the stellar surface out to several 100,000 kilometers, with temperatures ranging from a few thousand Kelvin at the outer edge to tens of millions of Kelvin near the inner boundary. The physics of accretion disks involves the interplay of gravity, rotation, pressure, and viscosity. Material in the disk orbits the central object at speeds determined by Kepler's laws, with inner regions completing orbits much faster than outer regions. This differential rotation creates shear between adjacent layers of gas, and viscous friction converts orbital energy into heat, while simultaneously transporting angular momentum outward. Without this viscous transport, material could not spiral inward, and the disk would simply orbit indefinitely without accreting onto the central object. The nature of this viscosity puzzled astrophysicists for decades. Ordinary molecular viscosity, the kind that makes honey flow slowly, is far too weak to explain the observed accretion rates in X-ray binaries. The solution came with the recognition that magnetic fields threading through the ionized gas can create an effective viscosity millions of times stronger than molecular processes. The magnetorotational instability, identified by Stephen Balbus and John Hawley in 1991, shows that even weak magnetic fields in a differentially rotating disk become unstable and amplify, creating turbulence that efficiently transports angular momentum. As material spirals inward through the disk, it releases gravitational potential energy at a rate that depends on how deep it falls into the gravitational well. For a neutron star with a mass of 1.4 solar masses and a radius of 10 kilometers, matter falling from infinity releases approximately 200 million electron volts per nucleon, converting roughly 20% of its rest mass energy into radiation. This efficiency far exceeds nuclear fusion, which converts less than 1% of mass into energy. The luminosity produced by accretion can reach values of 10 to the power of 31 watts, making X-ray binaries among the brightest individual sources in the galaxy at X-ray wavelengths. The temperature of the emitted radiation reflects the depth of the gravitational potential well. Near the inner edge of an accretion disk around a neutron star, temperatures reach 10 to 20 million Kelvin, producing thermal radiation that peaks in the X-ray band between 1 and 10 kilo-electron volts. This explains why these systems were first discovered not by optical telescopes, but by X-ray detectors flown above Earth's atmosphere, which absorbs cosmic X-rays. The Uhuru satellite, launched in 1970, catalogued over 300 X-ray sources during its 3-year mission, revealing a previously hidden population of accreting compact objects. X-ray binaries divide into 2 broad categories based on the mass of the companion star. High-mass X-ray binaries contain companions of 10 solar masses or more, typically young, hot stars that lose material through powerful stellar winds. The compact object captures a fraction of this wind, creating accretion that can be highly variable as the neutron star or black hole moves through regions of different density. The system Cygnus X1, discovered in 1964, exemplifies this class. Its companion is a blue supergiant star of approximately 20 solar masses, and the X-ray emission exhibits rapid flickering on time scales as short as milliseconds, indicating that the accreting object must be extremely compact. Low-mass X-ray binaries contain companions of roughly 1 solar mass or less, often evolved stars that have expanded to fill their Roche lobes. Mass transfer in these systems proceeds through the inner Lagrangian point, forming stable accretion disks that can persist for millions of years. The system Scorpius X1, the brightest persistent X-ray source in the sky outside the solar system, belongs to this class. Discovered in 1962 during a rocket flight that marked the birth of X-ray astronomy, Scorpius X1 accretes at a rate near the theoretical maximum, producing a luminosity of approximately 2.3 times 10 to the power of 31 watts. The maximum luminosity an accreting object can sustain is set by the balance between radiation pressure pushing outward and gravity pulling inward. This Eddington limit, named after Arthur Eddington, who first calculated it in 1926, depends on the mass of the accreting object and the opacity of the infalling material. For a neutron star accreting hydrogen-rich gas, the Eddington luminosity is approximately 1.8 times 10 to the power of 31 watts per solar mass of the accretor. When accretion attempts to exceed this rate, radiation pressure disrupts the inflow, creating instabilities that can produce dramatic X-ray bursts. Type 1 X-ray bursts occur when hydrogen and helium accumulate on the surface of an accreting neutron star until the pressure and temperature at the base of the accumulated layer trigger thermonuclear runaway. The flash consumes the fuel in a matter of seconds, releasing 10 to the power of 32 to 10 to the power of 33 joules of energy, and briefly increasing the X-ray luminosity by factors of 10 to 100. These bursts recur on timescales of hours to days, depending on the accretion rate. The burst profiles and recurrence times provide information about the neutron star's mass, radius, and surface composition, making them valuable tools for constraining the equation of state of ultra-dense matter. Some neutron stars in X-ray binaries possess magnetic fields strong enough to channel the accreting material onto the magnetic poles, rather than allowing it to spread across the surface through a disk. When the magnetic pressure exceeds the ram pressure of the infalling gas, accretion becomes magnetically controlled. This transition occurs at the Alfvén radius, which for a neutron star with a magnetic field of 10 to the power of 8 Tesla and an accretion rate near the Eddington limit, lies at approximately 100 kilometers from the stellar center. Inside this radius, material follows magnetic field lines to the poles, creating hot spots that produce pulsed X-ray emission as the star rotates. The accretion process in these systems can spin up the neutron star over time. Angular momentum carried by the infalling material is transferred to the star, gradually increasing its rotation rate. This mechanism explains the existence of millisecond pulses in binary systems, neutron stars that have been spun up to periods of a few milliseconds through billions of years of accretion. The fastest known pulsar, PSRJ 1748-2446 AD, rotates 716 times per second and almost certainly acquired this extreme spin through accretion from a companion star. Black holes in X-ray binaries present a different observational signature. Lacking a solid surface, they cannot produce thermonuclear bursts or magnetically channeled accretion columns. Instead, the accretion disk extends inward to the innermost stable circular orbit, a boundary set by general relativity beyond which no stable orbits exist. For a non-rotating black hole, this orbit lies at 3 times the Schwarzschild radius. Material crossing this boundary plunges into the event horizon within milliseconds, carrying its energy with it rather than radiating it away. The location of this inner edge, and thus the efficiency of energy extraction, depends on the black hole's spin, providing a method to measure this otherwise hidden property. The X-ray spectra of accreting black holes reveal both thermal emission from the disk and a power law component extending to much higher energies. This hard X-ray tail arises from inverse Compton scattering, where hot electrons in a corona above the disk boost the energy of thermal photons from the disk surface. The temperature of this corona can exceed 100 million Kelvin, and the resulting spectrum extends to energies of hundreds of kilo-electron volts. The relative strength of the thermal and power law components varies between different spectral states, reflecting changes in the geometry and physical conditions of the inner accretion flow. The spectral states of accreting black holes, with their shifting balance of thermal and power law emission, hint at a fundamental boundary that separates neutron stars from their darker cousins. This boundary, known as the Tolman-Oppenheimer-Volkoff limit, represents the maximum mass that any neutron star can sustain against gravitational collapse. Beyond this threshold, no known force in the universe can prevent matter from falling inward forever. The story of this limit begins with the same physics that governs the structure of white dwarfs, but carried to far more extreme conditions. In a white dwarf, electron degeneracy pressure, the quantum mechanical resistance of electrons to being squeezed into the same state, supports the star against gravity. Subramanian Chandrasekhar calculated in 1930 that this support fails when the white dwarf mass exceeds approximately 1.4 solar masses. Above this limit, electrons cannot move fast enough to provide adequate pressure without exceeding the speed of light, a physical impossibility that forces the star to collapse. Neutron stars face an analogous constraint, but the physics involves neutron degeneracy pressure rather than electron degeneracy. When a massive star's core collapses past the white dwarf stage, electrons are forced into protons through inverse beta decay, creating neutrons and releasing neutrinos. The resulting neutron-rich matter is supported primarily by the degeneracy pressure of neutrons, which are fermions, and thus obey the Pauli exclusion principle. Two neutrons cannot occupy the same quantum state, and this resistance to compression provides the pressure that halts gravitational collapse. Robert Oppenheimer and George Volkoff calculated the maximum mass for a neutron star in 1939, building on earlier work by Richard Tolman on the general relativistic structure of spherical matter distributions. Their calculation required solving the equations of hydrostatic equilibrium in the curved spacetime of general relativity, a significantly more complex problem than the Newtonian treatment adequate for white dwarfs. The key equation, now called the Tolman-Oppenheimer-Volkoff equation, describes how pressure must increase toward the center of a compact star to support the overlying layers against both gravity and the additional gravitational effect of the pressure itself. This last point deserves careful attention. In general relativity, pressure contributes to the gravitational field. Energy and momentum curve space-time, and pressure represents a form of energy density. In ordinary stars, this effect is negligible, but in neutron stars, where the central pressure can exceed 10 to the power of 34 pascals, the gravitational contribution of pressure becomes significant. This creates a subtle but crucial feedback. Higher pressure is needed to support the star, but higher pressure increases the gravitational pull, requiring still more pressure. This runaway effect ultimately limits how massive a neutron star can become. The original Oppenheimer-Volkoff calculation, using a simplified equation of state that treated neutrons as a non-interacting Fermi gas, yielded a maximum mass of approximately 0.7 solar masses. This value was troublingly low, barely half the Chandrasekhar limit for white dwarfs, and seemed to suggest that most collapsing stellar cores would form black holes rather than neutron stars. The resolution came from recognizing that neutrons in dense matter interact strongly through the nuclear force, and these interactions significantly stiffen the equation of state at high densities. The equation of state describes the relationship between pressure and density in matter, and it encapsulates all the complex physics of nuclear interactions. At densities below about 2 × 10⁻17 power kilograms per cubic meter, roughly the density of an atomic nucleus, The equation of state is reasonably well understood from laboratory nuclear physics. Neutrons and protons interact through the strong nuclear force, which is repulsive at very short distances and attractive at slightly larger separations. This repulsion at short range provides additional pressure support beyond simple degeneracy. At higher densities, the equation of state becomes increasingly uncertain. The matter in neutron star cores reaches densities of 5 to 10 times nuclear saturation density, conditions that cannot be replicated in terrestrial laboratories. Particle accelerator experiments can create matter at comparable energy densities, but only for fleeting instants and in tiny volumes, making it difficult to determine the equilibrium properties relevant to neutron star structure. Theoretical calculations must extrapolate from known physics into this uncharted regime. Different theoretical models for the high-density equation of state yield different predictions for the maximum neutron star mass. Soft equations of state, where pressure rises slowly with density, produce lower maximum masses, typically around 1.5 to 1.8 solar masses. Stiff equations of state, where pressure rises rapidly, can support neutron stars up to 2.5 or even 3 solar masses. The true equation of state lies somewhere in this range, and determining its properties has become one of the central goals of neutron star astrophysics. Observations have progressively constrained the equation of state by measuring the masses of actual neutron stars. The most massive, well-measured neutron stars include PSRJ 0348 plus 0432, with a mass of 2.01 plus or minus 0.04 solar masses, and PSRJ 0740 plus 6620, with a mass of 2.08 plus or minus 0.07 solar masses. These measurements immediately rule out the softest equations of state, which cannot support such massive objects. The equation of state must be stiff enough to sustain at least 2 solar masses against gravitational collapse. The measurement technique for these massive pulsars relies on relativistic effects in binary systems. PSRJ 0348 plus 0432 orbits a white dwarf companion with a period of just 2.46 hours, and the system exhibits a measurable Shapiro delay, the slowing of pulsar signals as they pass through the curved spacetime near the white dwarf. Combined with measurements of orbital decay due to gravitational wave emission, this allows precise determination of both component masses. PSRJ 0740 plus 6620 similarly orbits a white dwarf, and its mass was determined through a combination of Shapiro delay and pulse timing measurements spanning years of observation. The gravitational wave detection of the binary neutron-star merger GW170817 provided additional constraints on the equation of state. The gravitational wave signal encodes information about the tidal deformability of the neutron stars, how much they distort under each other's gravitational influence as they spiral together. Stiffer equations of state produce larger, more easily deformed neutron stars, while softer equations of state yield smaller, more compact objects. The observed signal indicated moderate tidal deformability, consistent with neutron star radii of approximately 11 to 13 kilometers for a 1.4 solar mass star. Current best estimates place the Tolman-Oppenheimer-Volkoff limit between 2.2 and 2.5 solar masses, though significant uncertainty remains. If the equation of state includes exotic phases of matter at the highest densities, perhaps free quarks no longer confined within neutrons, or strange quark matter containing strange quarks alongside up and down quarks, the maximum mass could be affected in ways that are difficult to predict from first principles. The existence of this maximum mass has profound implications for stellar evolution and the formation of black holes. When a massive star exhausts its nuclear fuel and its core collapses, the outcome depends on the core mass. Cores below the Tolman-Oppenheimer-Volkoff limit can form stable neutron stars, while those above must continue collapsing to form black holes. The supernova explosion that accompanies core collapse can eject varying amounts of matter, so the relationship between the initial stellar mass and the final compact object mass is complex and depends on details of the explosion mechanism. Observations suggest a possible gap in the mass distribution of compact objects, with few objects found between approximately 2.5 and 5 solar masses. Neutron stars cluster below the Tolman-Oppenheimer-Volkoff limit, while stellar mass black holes measured through X-ray binaries and gravitational wave detections typically exceed 5 solar masses. Whether this gap is real or an observational selection effect remains debated, but if real, it may reflect the physics of core collapse supernovae and the conditions required to form black holes of different masses. The Tolman-Oppenheimer-Volkoff limit thus marks a fundamental boundary in the universe, a threshold beyond which matter cannot resist its own gravity, regardless of its quantum mechanical properties. Below this limit, the Pauli exclusion principle and nuclear forces create stable configurations that can persist for billions of years. Above it, space-time itself becomes the dominant actor, curving so severely that no outward pressure can prevent the inexorable inward fall toward a singularity. When a massive star exhausts its nuclear fuel and its core exceeds this critical threshold, the collapse proceeds with a finality that no physical process can reverse. The iron core, having accumulated mass through successive stages of nuclear burning, reaches approximately 1.4 solar masses and begins its catastrophic implosion. Electron degeneracy pressure, which had supported the core against gravity, fails as electrons are forced to combine with protons through inverse beta decay. The core density climbs past 10 to the power of 14 grams per cubic centimeter, and for a brief moment, neutron degeneracy pressure halts the collapse, creating a proto-neutron star. But in the most massive progenitors, those stars that began their lives with 25 solar masses or more, the story does not end with a neutron star. The infalling material from the outer layers continues to rain down upon the nascent compact object, adding mass at rates that can exceed 1 solar mass per second. The proto-neutron star, already near the Tolman-Oppenheimer-Volkoff limit, cannot accommodate this additional burden. Within milliseconds to seconds of the initial bounce, the core mass surpasses the maximum that neutron degeneracy and nuclear forces can support, and a second collapse begins. This final collapse differs fundamentally from the first. There is no bounce, no outward shock wave, no mechanism to halt the inward fall. The matter that moments before existed as a sea of neutrons, quarks, and exotic particles simply continues to compress, its density climbing toward infinity. The escape velocity at the surface of the collapsing object increases, approaching and then exceeding the speed of light. At a radius of approximately 3 kilometers per solar mass of enclosed material, the escape velocity reaches 299,792 kilometers per second, and an event horizon forms. For a 10 solar mass black hole, this Schwarzschild radius measures roughly 30 kilometers. The matter that once constituted the stellar core, containing more mass than 10 of our suns, now occupies a region smaller than a mid-sized city. Yet the event horizon itself is not a physical surface, but a mathematical boundary, a sphere in space-time from which light cannot escape. An observer falling through this boundary would notice nothing remarkable at the moment of crossing, though they would be forever cut off from the universe outside. The formation timescale of a stellar mass black hole is astonishingly brief. From the moment the iron core begins its collapse to the formation of the event horizon, less than 1 second typically elapses. The outer layers of the star may not even be aware of the catastrophe unfolding at the center. In some cases, particularly for the most massive progenitors with initial masses exceeding 40 solar masses, the collapse proceeds so rapidly and completely that no supernova explosion occurs at all. The star simply vanishes, its outer envelope swallowed by the growing black hole in what astronomers call a failed supernova or direct collapse. Observations of such events remain challenging but not impossible. The star N6946-BH1 in the galaxy NGC 6946, located approximately 22 million light-years from Earth, provided compelling evidence for this process. This red supergiant, with an estimated mass of 25 solar masses, brightened modestly in 2009 before fading below detectability. No supernova was observed, yet the star had clearly disappeared. The most plausible explanation is that its core collapsed directly to a black hole with insufficient energy to unbind the stellar envelope through a conventional explosion. The physics governing which massive stars produce neutron stars and which produce black holes depends on multiple factors beyond simple initial mass. The metallicity of the star, meaning its abundance of elements heavier than helium, affects mass loss through stellar winds over the star's lifetime. A metal-rich star may shed substantial mass before core collapse, potentially reducing its final core mass below the threshold for black hole formation. Conversely, metal-poor stars retain more of their original mass, making direct collapse more likely. Rotation also plays a crucial role. A rapidly spinning core possesses angular momentum that must be conserved during collapse. This angular momentum can provide centrifugal support against gravity, potentially delaying or preventing black hole formation in some cases. However, if the angular momentum is too high, the collapsing material may form an accretion disk around the nascent black hole rather than falling directly in, leading to the energetic phenomena associated with gamma-ray bursts. The collapsar model, developed to explain long-duration gamma-ray bursts, describes precisely this scenario. A massive, rapidly rotating star collapses to form a black hole surrounded by a thick accretion disk. Material spiraling inward through this disk releases gravitational potential energy at extraordinary rates, with temperatures in the inner disk exceeding 10 to the power of 10 Kelvin. Neutrino annihilation and magnetic processes extract energy from this system, launching relativistic jets along the rotation axis at speeds exceeding 99.9% of light speed. These jets, if they successfully punch through the stellar envelope, produce the gamma-ray bursts detected by satellites such as SWIFT and Fermi. The burst GRB 030329, observed in March 2003 at a distance of approximately 2.6 billion light-years, provided direct evidence linking long gamma-ray bursts to the deaths of massive stars. Spectroscopic observations of its afterglow revealed signatures of a Type 1c supernova, confirming that the burst originated from the core collapse of a massive star that had lost its hydrogen and helium envelopes. The mass distribution of stellar black holes formed through these processes carries information about the physics of core collapse and the properties of massive star populations. Gravitational wave observations by LIGO and Virgo have detected black holes with masses ranging from approximately 5 solar masses to over 80 solar masses. The detection GW150914, the first direct observation of gravitational waves, involved the merger of 2 black holes with masses of 36 and 29 solar masses, producing a final black hole of 62 solar masses. The missing 3 solar masses were radiated away as gravitational wave energy in a fraction of a second. The existence of black holes with masses exceeding 50 solar masses presents theoretical challenges. Pair instability supernovae, which occur when the cores of very massive stars become hot enough for photons to convert into electron-positron pairs, should completely disrupt stars in certain mass ranges, leaving no remnant at all. This process is expected to create a gap in the black hole mass distribution between approximately 50 and 130 solar masses. Yet LIGO has detected black holes within this forbidden range, suggesting either that our understanding of pair instability physics is incomplete, or that these black holes formed through mergers of smaller black holes, rather than direct stellar collapse. The environment in which a massive star dies also influences the outcome. In dense stellar clusters, where stars are packed thousands of times more closely than in the solar neighborhood, dynamical interactions can pair black holes together long after their formation. These binary black holes, brought together by gravitational encounters with other cluster members, eventually spiral inward and merge, potentially producing black holes in mass ranges that single-star evolution cannot access. The formation of stellar mass black holes represents the ultimate victory of gravity over all other forces. The strong nuclear force, which binds protons and neutrons together, cannot prevent the collapse. The electromagnetic force, responsible for the rigidity of ordinary matter, becomes irrelevant at nuclear densities. Even the quantum mechanical degeneracy pressure that supports white dwarfs and neutron stars eventually yields to gravitational compression. What remains is pure space-time geometry, curved so severely that it traps everything, including light itself, within a boundary from which there is no return. That boundary, the surface beyond which light itself becomes imprisoned, emerges naturally from the mathematics of general relativity. In 1916, just months after Einstein published his field equations describing how mass and energy curve space-time, the German physicist Karl Schwarzschild derived an exact solution while serving on the Russian front during World War I. Working in the trenches, suffering from a painful autoimmune disease that would claim his life within the year, Schwarzschild found the geometry of space-time surrounding a perfectly spherical, non-rotating mass. His solution revealed something unexpected. At a specific radius, the mathematics produced a coordinate singularity, where certain terms in the equations became infinite or zero. This radius, now bearing his name, defines the event horizon of what we call a Schwarzschild black hole. The Schwarzschild radius depends only on the mass of the object, following a remarkably simple formula. For any mass m, this critical radius equals 2gm divided by the speed of light squared, where g is Newton's gravitational constant. For the Sun, this works out to approximately 2.95 kilometers. If somehow the entire solar mass could be compressed within a sphere of this radius, it would become a black hole. For the Earth, the Schwarzschild radius is merely 8.87 millimeters, roughly the size of a small marble. A 10 solar mass black hole, typical of those formed from stellar collapse, possesses an event horizon with a radius of about 30 kilometers, comparable to the size of a small city. The supermassive black hole at the center of our galaxy, Sagittarius A star, with its 4 million solar masses, has a Schwarzschild radius of approximately 12 million kilometers, about 17 times the radius of the Sun. The Schwarzschild metric describes how distances and time intervals change as one approaches this boundary. Far from the black hole, where gravity is weak, space-time appears nearly flat, and the familiar rules of special relativity apply. Clocks tick at their normal rate, rulers measure their expected lengths, and light travels along straight paths. But as one moves closer to the event horizon, these comfortable certainties begin to dissolve. The metric reveals that time, as measured by a distant observer, slows down for objects approaching the horizon. This gravitational time dilation becomes increasingly severe, following a factor that depends on the ratio of the Schwarzschild radius to the actual distance from the center. Consider a clock falling toward a 10 solar mass black hole. When this clock reaches a distance of 300 kilometers from the center, 10 times the Schwarzschild radius, it ticks at about 95% of its normal rate as seen by a distant observer. At 60 kilometers, twice the Schwarzschild radius, the clock runs at only 71% of its distant rate. At 33 kilometers, just 10% above the horizon, time has slowed to 32% of normal. And as the clock approaches the event horizon itself, at 30 kilometers, its ticking rate approaches zero from the perspective of anyone watching from afar. The clock appears to freeze, its final moments stretching toward infinity. This time dilation has profound consequences for what distant observers can actually see. Light emitted by an object falling toward a black hole must climb out of an increasingly deep gravitational well. As the object approaches the horizon, photons lose more and more energy in this climb, their wavelengths stretching toward the red end of the spectrum and beyond into the infrared, microwave, and radio bands. Simultaneously, the rate at which photons arrive at a distant telescope decreases, because time near the horizon runs so slowly. An infalling astronaut, from their own perspective, would cross the event horizon in finite time, perhaps a few hundred microseconds for a stellar mass black hole, but to observers watching from a safe distance, that same astronaut would appear to slow down asymptotically, growing dimmer and redder, never quite reaching the horizon even after waiting for billions of years. The event horizon itself is not a physical surface. No material barrier exists there, no wall or membrane that an infalling object would strike. Instead, it represents a boundary in space-time geometry, a point of no return defined purely by the curvature of space and time. Inside this radius, the radial coordinate, which outside the horizon represents distance from the center, takes on the mathematical properties of time. The singularity at the center becomes not a place in space, but a moment in the future, as inevitable and inescapable as tomorrow. Every trajectory, whether followed by matter or light, leads inexorably toward this central point, just as every moment in ordinary life leads toward the future. The proper distance to the event horizon, measured by an observer actually making the journey, differs from the coordinate distance that appears in the Schwarzschild metric. For someone falling freely from rest at a great distance, the trip to the horizon of a 10 solar mass black hole takes only about 0.2 milliseconds of their own experienced time once they pass within 100 kilometers. The journey feels brief, almost instantaneous. Yet during this short interval, the infalling observer would see the external universe age dramatically. Light from distant stars, blue shifted by the observer's increasing velocity and the gravitational field, would compress into an ever-brightening ring around the black hole's silhouette. The entire future history of the cosmos would unfold in those final moments, though the practical limits of human perception and survival would prevent any actual witnessing of this cosmic fast-forward. At the event horizon, the escape velocity equals the speed of light, 299,792 kilometers per second. This is the defining characteristic of the boundary. Below this surface, escaping would require traveling faster than light, which relativity forbids for any object with mass or for light itself. Photons emitted exactly at the horizon, aimed directly outward, would hover forever, neither escaping nor falling inward, trapped on the knife edge of the gravitational well. Photons emitted just inside the horizon, no matter their initial direction, would find themselves dragged inward, their world lines bent by the extreme curvature until they point toward the singularity. The surface gravity at the event horizon, a measure of the gravitational acceleration experienced by a stationary observer there, takes a value that seems almost paradoxically gentle for stellar mass black holes. For a 10 solar mass black hole, this surface gravity equals approximately 1.5 trillion meters per second squared, about 150 billion times Earth's surface gravity. Yet this number, while enormous by terrestrial standards, is finite and well-defined. The surface gravity actually decreases for more massive black holes, scaling inversely with mass. Sagittarius A star, despite its 4 million solar masses, has a surface gravity at its horizon of only about 9,400 meters per second squared, less than 1,000 times Earth's gravity. This counterintuitive result arises because the horizon radius grows linearly with mass, while the gravitational acceleration at a given radius decreases with the square of the distance. The tidal forces near the horizon tell a different story. These forces, arising from the difference in gravitational pull between the near and far sides of an extended object, determine whether an infalling traveler would be stretched and compressed, a process colorfully termed spaghettification. For stellar mass black holes, tidal forces become lethal well outside the event horizon. An astronaut falling toward a 10 solar mass black hole would be torn apart at roughly 400 kilometers from the center, more than 13 times the Schwarzschild radius. The tidal acceleration at this distance would exceed the tensile strength of human tissue, pulling the head and feet apart while squeezing the body from the sides. For supermassive black holes, however, the tidal forces at the horizon are far gentler. A traveler crossing the event horizon of Sagittarius A star would experience tidal accelerations of only about 0.001 meters per second squared per meter of body length. Barely noticeable. They would pass the point of no return without any immediate physical sensation, realizing their fate only when attempts to communicate with the outside universe failed and the singularity loomed ahead. The geometry of space-time itself becomes the protagonist in the final approach toward a black hole's center. What began as a subtle warping far from the event horizon transforms into something far more extreme, a curvature so intense that the very concepts of space and time lose their familiar meanings. The mathematics that describes this distortion reveals a universe where the rules governing everyday experience break down completely, replaced by a geometry that bends all paths inexorably toward a single destination. Geodesics, the paths that objects follow when moving freely through space-time, provide the clearest window into this strange realm. In flat space-time, far from any massive object, geodesics are simple straight lines. A particle released at rest remains at rest, and a particle in motion continues along its trajectory unchanged. But near a black hole, geodesics curve and twist in response to the warped geometry. The straightest possible path through curved space-time is no longer straight in the ordinary sense. It bends toward the source of curvature, and inside the event horizon, every geodesic, without exception, terminates at the singularity. The Schwarzschild geometry provides the mathematical framework for understanding these paths. In the coordinates typically used to describe a non-rotating black hole, the metric takes a specific form that encodes how distances and time intervals relate to one another at every point. The coefficient in front of the time component changes sign at the Schwarzschild radius, a mathematical signature of the event horizon. Inside this boundary, what was previously the radial coordinate, measuring distance from the center, takes on the mathematical properties of time. The singularity at the center is not a place in space that one might avoid by steering around it. It is a moment in the future, as unavoidable as tomorrow. This interchange of space and time inside the horizon has profound implications for any object that crosses it. Outside the event horizon, an observer can choose to move toward or away from the black hole. They possess freedom in the radial direction, just as they possess freedom to move forward or backward along a road. But inside the horizon, the radial direction becomes time-like, and just as no one can choose to move backward in time, no one can choose to move away from the singularity. Every possible trajectory, every geodesic, leads inward. The singularity lies in the future of every event inside the horizon, separated from the present by an interval of proper time that depends on where the object entered and how it moves. For an object falling radially into a Schwarzschild black hole from rest at the event horizon, the proper time to reach the singularity is remarkably brief. The formula yields a time of approximately 15 microseconds, multiplied by the mass of the black hole in solar masses. For a 10 solar mass stellar black hole, this amounts to roughly 150 microseconds, less than 2/10,000ths of a second. For Sagittarius A star, with its 4 million solar masses, the journey from horizon to singularity takes about 60 seconds. These numbers represent the maximum survival time for an infalling observer. Attempting to accelerate, to fire rockets in any direction, only shortens this interval. The geometry is unforgiving. Fighting against it consumes proper time without changing the ultimate destination. The curvature of space-time near the singularity grows without bound. Physicists quantify this curvature using the Riemann tensor, a mathematical object with 20 independent components that fully describes how space-time bends at each point. From the Riemann tensor, one can construct scalar quantities, single numbers that characterize the overall intensity of curvature. The Kretschmann scalar, formed by contracting the Riemann tensor with itself, provides one such measure. For a Schwarzschild black hole, this scalar equals 48 times the gravitational constant squared times the mass squared, divided by the speed of light to the 4th power and the radial coordinate to the 6th power. As the radial coordinate approaches 0, the Kretschmann scalar diverges to infinity. The curvature becomes genuinely singular, not merely large, but mathematically unbounded. This divergence signals the breakdown of classical general relativity. The theory predicts its own failure, indicating that quantum gravitational effects must become important as the singularity is approached. At distances comparable to the Planck length, approximately 1.6 times 10 to the negative 35 meters, the smooth space-time manifold assumed by general relativity likely gives way to something else entirely. Quantum fluctuations in the geometry itself may become dominant. Space and time may lose their continuous character, perhaps becoming discrete or foamy at these scales. No complete theory of quantum gravity yet exists to describe what happens at the singularity, leaving the ultimate fate of infalling matter shrouded in theoretical uncertainty. The tidal forces experienced by an extended object grow in proportion to the curvature. Near the singularity, these forces become catastrophic. The stretching in the radial direction and compression in the transverse directions intensify without limit. Any material object, regardless of its composition or structural strength, will be torn apart and compressed into an infinitely thin stream. This process, sometimes called spaghettification, represents the physical manifestation of the diverging curvature. The atoms themselves are stripped apart, their electrons separated from nuclei, and eventually the nuclei themselves may be disrupted as the tidal forces exceed the strong nuclear force. Null geodesics, the paths followed by light rays, exhibit equally striking behavior inside the horizon. light emitted by an infalling object cannot escape to the outside universe. But more than that, light emitted radially outward inside the horizon actually moves toward the singularity, not away from it. The geometry has become so distorted that outward-directed light rays have negative radial velocity in the usual coordinates. They move inward toward smaller radial values, even though they are aimed outward. This counterintuitive behavior reflects the fundamental change in the nature of the radial direction inside the horizon. The photon sphere, located at 1.5 times the Schwarzschild radius for a non-rotating black hole, marks the boundary where light can orbit the black hole on unstable circular paths. At exactly this radius, 30 kilometers for a 10 solar mass black hole, photons can circle the singularity indefinitely, though any slight perturbation will send them either spiraling inward or escaping outward. Inside the photon sphere but outside the horizon, light can still escape if directed sufficiently outward, but the required angle becomes increasingly steep. At the event horizon itself, only light directed exactly radially outward can momentarily hover, and even that light makes no progress in escaping. The embedding diagrams often used to visualize curved space-time become increasingly misleading near the singularity. These diagrams, which show a two-dimensional surface curved in three-dimensional space, can represent the spatial geometry at a moment of time outside the horizon. The familiar funnel shape, stretching downward toward the black hole, captures something of the curvature. But inside the horizon, where the radial direction becomes time-like, such static representations fail. The geometry is inherently dynamic, with the singularity representing not a place, but a time. Visualizing this requires thinking in terms of space-time diagrams, where the future light cones of all events inside the horizon tilt so severely that they all point toward the singularity. The assumption of perfect spherical symmetry, while mathematically elegant, represents an idealization that nature rarely achieves. Real stars rotate. They carry angular momentum accumulated over billions of years of gravitational contraction, and when they collapse into black holes, that angular momentum cannot simply vanish. Conservation laws demand its preservation, and the resulting objects differ profoundly from their non-rotating counterparts. The geometry of a rotating black hole, first described by Roy Kerr in 1963, reveals a space-time structure far richer and stranger than Schwarzschild could have imagined. Kerr's solution to Einstein's field equations required 17 years of effort by the mathematical physics community after Schwarzschild's original work. The added complexity of rotation transforms the problem from one involving a single parameter, mass, to one requiring two, mass and angular momentum. The angular momentum of a black hole is typically expressed as a dimensionless spin parameter, the ratio of the actual angular momentum to the maximum possible for a given mass. This parameter ranges from 0, for a non-rotating Schwarzschild black hole, to 1, for a maximally spinning Kerr black hole. Observations of stellar mass black holes in X-ray binaries suggest spin parameters spanning this entire range, with some objects like Cygnus X, one showing values around 0.97, spinning at nearly the theoretical maximum. The geometry of a Kerr black hole differs fundamentally from its spherically symmetric cousin. The event horizon, rather than being a perfect sphere, becomes an oblate spheroid, flattened at the poles and bulging at the equator. For a black hole of 10 solar masses with a spin parameter of 0.9, the equatorial radius of the event horizon shrinks to approximately 14.4 kilometers, compared to the 30-kilometer Schwarzschild radius of a non-rotating black hole of the same mass. The faster the spin, the smaller the horizon becomes, approaching a limiting configuration where the horizon radius equals half the Schwarzschild value for maximal rotation. More remarkable than the horizon's shape is the emergence of a new region of space-time called the ergosphere. This zone extends outside the event horizon, bounded by a surface known as the static limit. Within the ergosphere, space-time itself is dragged around by the black hole's rotation with such ferocity that remaining stationary becomes physically impossible. Not merely difficult, but forbidden by the geometry of space-time itself. Even a particle with infinite thrust, attempting to hover at a fixed position within the ergosphere, would find itself swept along in the direction of the black hole's rotation. The static limit touches the event horizon at the poles and extends farthest at the equator, creating a region shaped somewhat like a flattened pumpkin surrounding the inner spheroid of the horizon. This dragging of space-time, called frame dragging or the lens-Thirring effect, represents one of the most counterintuitive predictions of general relativity. Near a rotating black hole, the effect becomes extreme, but it exists around any rotating mass. Earth itself drags space-time as it spins, though the effect is minuscule. The Gravity Probe B satellite, launched in 2004, measured this frame dragging around Earth with exquisite precision, detecting a precession of its gyroscopes by just 37 milliarcseconds per year, confirming Einstein's prediction to within 0.2% accuracy. Near a rapidly spinning black hole, the same physics operates at scales billions of times more intense. The mathematics of the Kerr metric introduces coordinates that reflect the axial symmetry of the rotating space-time. Unlike the Schwarzschild geometry, where all directions perpendicular to the radial are equivalent, the Kerr geometry distinguishes the equatorial plane from the polar regions. Orbits around a Kerr black hole depend not only on distance, but on inclination relative to the spin axis. Particles orbiting in the same direction as the black hole's rotation, prograde orbits, can approach closer to the horizon than particles in retrograde orbits, moving against the rotation. For a maximally spinning black hole, the innermost stable circular orbit for prograde motion lies at just 1.24 times the gravitational radius, while retrograde orbits must remain beyond 9 times this distance. This asymmetry between prograde and retrograde orbits has profound implications for accretion physics. Material spiraling inward through an accretion disk around a rapidly spinning black hole can release far more gravitational potential energy before plunging through the horizon. For a Schwarzschild black hole, the binding energy at the innermost stable orbit corresponds to about 5.7% of the rest mass energy. For a maximally spinning Kerr black hole with prograde accretion, this efficiency rises to approximately 42%. This means that matter falling into a rapidly spinning black hole can convert nearly half its mass into radiated energy before disappearing, making spinning black holes the most efficient engines for converting matter to energy in the known universe. The interior structure of a Kerr black hole differs dramatically from the Schwarzschild case. Rather than a single-point singularity, the rotating black hole contains a ring singularity, a circle of infinite curvature lying in the equatorial plane. The radius of this ring equals the angular momentum divided by the mass times the speed of light. For a 10 solar mass black hole spinning at 90% of maximum, this ring has a radius of approximately 13.5 kilometers. Remarkably, the mathematical solution suggests that an observer falling along the rotation axis could pass through the center of this ring without encountering the singularity itself, though the physical reality of this possibility remains deeply uncertain. The Kerr solution also reveals the existence of an inner horizon, a second null surface lying between the outer event horizon and the ring singularity. This inner horizon, also called the Cauchy horizon, marks a boundary beyond which the deterministic evolution of physics breaks down. Observers crossing this surface would encounter the accumulated radiation of the entire future history of the external universe, blue shifted to arbitrarily high energies. Whether this inner horizon survives as a physical feature in realistic rotating black holes, or whether quantum effects and perturbations destroy it, remains an active area of theoretical research. The process by which black holes acquire their spin connects to their formation and subsequent evolution. When massive stars collapse, they typically possess significant angular momentum, and much of this momentum becomes trapped within the forming black hole. Subsequent accretion can either spin up or spin down the black hole depending on the orientation of the infalling material. Prolonged accretion from a disk aligned with the black hole's rotation tends to increase the spin toward the maximum value, while misaligned or chaotic accretion can reduce it. The observed distribution of black hole spins in X-ray binaries suggests that both formation processes and accretion history contribute to the final spin values. The ergosphere of a rotating black hole enables a remarkable phenomenon first identified by Roger Penrose in 1969. A particle entering the ergosphere can split into two fragments, with one fragment falling into the black hole on a trajectory that carries negative energy as measured from infinity, while the other fragment escapes with more energy than the original particle possessed. This Penrose process extracts rotational energy from the black hole, slightly reducing its spin. The maximum efficiency of this process allows extraction of up to 29% of the black hole's total mass energy, corresponding to the rotational energy of a maximally spinning hole. While individual particle interactions of this type are unlikely to occur naturally with significant frequency, the magnetic fields threading accretion disks may enable analogous processes that power the relativistic jets observed from active galactic nuclei. Frame dragging affects not only matter, but light itself. Photons passing near a rotating black hole have their trajectories bent not only toward the mass, but also twisted in the direction of rotation. This gravitomagnetic effect causes the shadow of a rotating black hole, the dark silhouette seen against background light, to appear asymmetric. One side of the shadow, where light orbits in the prograde direction, appears slightly smaller and brighter, while the opposite side extends farther and appears dimmer. The Event Horizon Telescope observations of the supermassive black hole in M87, with its asymmetric ring of emission, provide indirect evidence of this frame-dragging effect, though disentangling the contributions of space-time geometry from those of the plasma physics remains challenging. The plasma itself, swirling around that rotating black hole, tells its own story through the physics of accretion. Matter does not simply fall straight into a black hole. Conservation of angular momentum, that fundamental principle governing all rotating systems, forces infalling material to spiral inward along ever-tightening orbits, forming the luminous structures known as accretion disks. These disks, some spanning millions of kilometers, others stretching across distances comparable to our entire solar system, represent some of the most efficient energy-generating mechanisms in the universe, converting gravitational potential energy into radiation with efficiencies that dwarf nuclear fusion. The journey of a single hydrogen atom toward a stellar mass black hole illustrates the physics at work. Captured from a companion star or drawn from the interstellar medium, this atom initially orbits at distances where the black hole's gravity, while dominant, allows relatively leisurely circular motion. At 10,000 Schwarzschild radii from a 10-solar mass black hole, roughly 300,000 kilometers out, the orbital velocity reaches approximately 3,000 kilometers per second. The atom circles the black hole once every few seconds, part of a vast ring of material all moving at similar speeds. But this orderly circulation cannot persist indefinitely. The key to understanding accretion lies in viscosity, the internal friction within the disk that allows angular momentum to be transported outward while mass spirals inward. In ordinary fluids, molecular viscosity arises from collisions between particles. But in the tenuous plasma of an accretion disk, this molecular viscosity proves far too weak to explain the observed accretion rates. A disk relying solely on molecular viscosity would take longer than the age of the universe to feed significant mass into a stellar mass black hole. Something else must be at work, some mechanism that creates effective friction on scales far larger than individual particle interactions. The answer lies in turbulence, specifically magneto-hydrodynamic turbulence driven by the magneto-rotational instability. Discovered theoretically by Evgeny Velikov in 1959 and independently by Stephen Balbus and John Hawley in 1991 in the astrophysical context, this instability arises whenever a weak magnetic field threads a differentially rotating disk. The inner regions of an accretion disk orbit faster than the outer regions, a consequence of Kepler's laws applied to the black hole's gravitational field. At 3 Schwarzschild radii, material orbits at roughly half the speed of light, while at 30 Schwarzschild radii, the orbital velocity drops to about 15% of light speed. This differential rotation, combined with even a modest magnetic field, creates an instability that amplifies turbulent motions throughout the disk. The mechanism operates through magnetic tension. Imagine 2 parcels of gas at slightly different radii, connected by a magnetic field line. The inner parcel orbits faster and pulls ahead, stretching the field line between them. This stretched field acts like a spring, pulling backward on the inner parcel and forward on the outer one. the inner parcel loses angular momentum and falls to a smaller orbit, while the outer parcel gains angular momentum and moves outward. This exchange amplifies the original perturbation, driving ever stronger turbulence that efficiently transports angular momentum outward through the disk. The resulting turbulent viscosity, characterized by the dimensionless parameter alpha introduced by Nikolai Shakura and Rashid Sunyaev in 1973, typically ranges from 0.01 to 0.1 in most accretion disks. This parameterization, while hiding the complex magnetohydrodynamics behind a single number, allows astrophysicists to model disk structure and predict observable properties. The alpha parameter essentially measures how efficiently the turbulence converts orbital energy into heat, with higher values indicating more vigorous angular momentum transport and faster accretion. As material spirals inward through this turbulent medium, gravitational potential energy converts into thermal energy through viscous dissipation. The temperature structure of the disk follows predictable patterns, rising steeply towards the inner edge where gravitational forces intensify. For a disk around a 10 solar mass black hole accreting at 10% of the Eddington limit, the temperature at 100 Schwarzschild radii reaches approximately 1 million Kelvin. Closer in, at 10 Schwarzschild radii, temperatures climb to several million Kelvin. At the innermost stable circular orbit, located at 6 Schwarzschild radii for a non-rotating black hole, or as close as 1.24 Schwarzschild radii for a maximally spinning Kerr black hole, temperatures can exceed 10 million Kelvin. These temperatures determine the radiation emitted by the disk. A patch of disk surface at 1 million Kelvin radiates predominantly in the extreme ultraviolet, with photon energies around 100 electron volts. Hotter regions closer to the black hole emit soft X-rays, with characteristic energies of 1 to 2 kiloelectron volts. The integrated spectrum of the entire disk, combining contributions from all radii, produces the distinctive multi-temperature blackbody spectrum observed from many accreting black holes. This spectrum rises toward higher energies following a power law, then curves over and declines exponentially at energies corresponding to the hottest inner disk regions. The geometry of the disk affects how this radiation reaches distant observers. Standard thin disk models, applicable when the accretion rate remains well below the Eddington limit, assume the disk maintains a thickness much smaller than its radius, typically a few percent. The disk surface radiates approximately as a black body at each radius, with the local temperature determined by the balance between viscous heating and radiative cooling. The total luminosity of such a disk scales with the accretion rate and the depth of the gravitational potential well, reaching efficiencies of roughly 6% for non-rotating black holes and up to 42% for maximally rotating ones. This efficiency deserves emphasis. Nuclear fusion in stellar cores converts approximately 0.7% of rest mass energy into radiation. Accretion onto a Kerr black hole achieves efficiencies 60 times greater, making these systems the most efficient steady-state energy sources known to physics. A single solar mass of material accreting onto a rapidly rotating stellar mass black hole releases energy equivalent to the total output of the Sun over its entire 10 billion-year main sequence lifetime. The inner edge of the disk marks a critical transition. Inside the innermost stable circular orbit, no stable circular orbits exist. Material that crosses this boundary plunges rapidly towards the event horizon, completing its final spiral in a fraction of a second. The radiation emitted during this plunge contributes to the observed spectrum, but in ways that depend sensitively on the black hole's spin and the detailed physics of the plunging region. Some models predict a sharp truncation of emission at the innermost stable orbit, while others suggest continued radiation from the plunging material, creating subtle spectral signatures that encode information about the space-time geometry. Observations of X-ray binary systems, where stellar mass black holes accrete from companion stars, reveal these disk physics in action. The system Cygnus X1, containing a black hole of approximately 21 solar masses orbiting a blue supergiant star, shows the characteristic thermal disk spectrum during its soft state, with temperatures around 2 million Kelvin indicating emission from the inner disk regions. Spectral fitting of this thermal component, accounting for relativistic effects near the spinning black hole, suggests the disk extends down to radii consistent with a black hole spin parameter of at least 0.95, meaning the innermost stable orbit lies at roughly 2 Schwarzschild radii rather than 6. The disk does not exist in isolation. Above and below the relatively cool disk mid-plane, a corona of extremely hot electrons, with temperatures reaching hundreds of millions of Kelvin, Comptonizes the thermal disk photons. Soft X-ray photons from the disk scatter off these energetic electrons, gaining energy with each collision until they emerge as hard X-rays with energies of tens to hundreds of kilo-electron volts. This Comptonization process produces the power law spectral component observed in many accreting black holes, with the spectral index encoding information about the optical depth and temperature of the corona. The corona, however, represents only one destination for the energy liberated by accretion. Some black holes channel a fraction of their gravitational power into structures far more dramatic and far-reaching than any thermal emission from the disk itself. Twin beams of plasma, collimated into narrow jets, can extend outward from the polar regions at velocities approaching 99% the speed of light, carrying energy across distances of millions of light-years before finally dissipating into the intergalactic medium. These relativistic jets represent one of the most efficient energy transport mechanisms in the universe. The jet emanating from the supermassive black hole in Messier 87, first photographed as a luminous streak by Heber Curtis in 1918, extends across 5,000 light-years of space, its blue synchrotron glow betraying the presence of electrons spiraling through magnetic fields at relativistic speeds. The total power carried by this single jet exceeds 10 to the 44th watts, roughly 1 trillion times the luminosity of the Sun, sustained continuously for millions of years. The mechanism responsible for launching these jets remained mysterious for decades after their discovery. The accretion disk itself, despite its enormous energy output, cannot easily explain the extreme collimation and relativistic velocities observed. Thermal pressure from hot gas would produce spherical outflows, not tightly focused beams. Radiation pressure, while capable of driving winds, lacks the geometry to create jets with opening angles of only a few degrees. The solution? proposed by Roger Blandford and Roman Zanarjek in 1977, draws power not from the accretion disk directly, but from the rotational energy of the black hole itself. A spinning black hole, described by the Kerr metric, possesses an ergosphere where space-time rotates so rapidly that no object can remain stationary relative to distant observers. Within this region, magnetic field lines threading the event horizon become twisted by the frame dragging effect, their footpoints forced to rotate with the black hole's spin. This rotation of magnetic field lines creates an electromagnetic analog of a unipolar inductor, the same principle that generates current when a conducting disk spins in a magnetic field. The voltage difference between the pole and equator of a rapidly spinning black hole, threaded by magnetic fields of 10 to the 4th Tesla, can reach 10 to the 20 volts. Charged particles, primarily electrons and positrons created by photon-photon collisions in the intense radiation field near the horizon, experience this electric field and accelerate outward along the polar magnetic field lines. The power extracted through the Blandford-Zanarjek mechanism depends on the product of the magnetic field strength squared, the black hole mass squared, and a function of the spin parameter that vanishes for non-rotating black holes and approaches unity for maximally spinning ones. For a black hole of 10 solar masses with a spin parameter of 0.9 and magnetic fields of 10 to the 8th Tesla near the horizon, the extractable power reaches approximately 10 to the 38 watts. For the supermassive black hole in M87, with its mass of 6.5 billion solar masses, the available power scales upward to match the observed jet luminosity. The magnetic fields required for this process do not arise spontaneously from the black hole itself, which, according to the no-hair theorem, can possess only mass, charge, and angular momentum. Instead, the accretion disk serves as the source, its turbulent magnetohydrodynamic flows, amplifying seed fields through differential rotation and the magnetorotational instability. Field lines anchored in the disk are advected inward with the accreting plasma, accumulating near the event horizon until they reach the strengths necessary for efficient jet launching. The geometry of these accumulated fields determines the jet structure. Magnetic field lines threading the event horizon near the poles extend outward along the rotation axis, their tension providing the hoop stress that collimates the outflowing plasma. The Lorentz force, arising from the interaction of currents flowing along the jet with the toroidal magnetic field component, accelerates the plasma while simultaneously confining it to a narrow channel. This magnetohydrodynamic collimation becomes increasingly effective at larger distances, explaining why jets often appear more tightly focused far from their launching point than near the black hole itself. The plasma within these jets achieves bulk Lorentz factors of 10 to 50 in many active galactic nuclei, meaning the jet material moves so close to light speed that time dilation factors reach similar values. For the jets in blazars, where our line of sight happens to align with the jet axis, Doppler boosting amplifies the observed luminosity by factors of thousands, making these objects visible across cosmological distances despite their intrinsically modest power output compared to the most luminous quasars. Observations with very long baseline interferometry have resolved the jet launching region in M87 down to scales of a few Schwarzschild radii. The Event Horizon Telescope collaboration, famous for producing the first image of a black hole shadow, has also mapped the magnetic field structure near the base of the M87 jet, revealing a predominantly poloidal geometry consistent with the Blandford-Znajek mechanism. The polarization patterns in the ring of emission surrounding the shadow indicate magnetic field strengths of 1 to 30 Gauss at distances of a few gravitational radii, sufficient to power the observed jet when combined with the black hole's spin. Not all accreting black holes produce powerful jets. The transition between jet-dominated and disk-dominated states appears to depend on the accretion rate relative to the Eddington limit, the magnetic flux accumulated near the horizon, and the black hole spin. Stellar mass black holes in X-ray binary systems cycle through different spectral states over timescales of weeks to months, with jets appearing prominently in the hard state when the accretion rate is low and the inner disk may be geometrically thick, then suppressing as the source transitions to the soft state, with a geometrically thin disk extending close to the innermost stable orbit. The jets themselves emit radiation across the entire electromagnetic spectrum through synchrotron and inverse Compton processes. Electrons spiraling in the jet's magnetic field radiate synchrotron photons from radio wavelengths through optical and into X-rays, with the spectral shape encoding information about the electron energy distribution and magnetic field strength. These same electrons can scatter ambient photons, including synchrotron photons from elsewhere in the jet, to gamma-ray energies through the inverse Compton mechanism, producing the high-energy emission detected by space telescopes like Fermi. At the largest scales, jets eventually decelerate through interaction with the surrounding medium, inflating enormous lobes of relativistic plasma that can span megaparsecs. The radio galaxy Alcyonius, discovered in 2022, possesses lobes extending across nearly 17 million light-years, making it the largest known structure created by a single galaxy. These lobes represent the accumulated energy output of the central black hole over hundreds of millions of years, their radio emission slowly fading as the electrons lose energy to synchrotron radiation and inverse Compton scattering off the cosmic microwave background. The engines powering those immense lobes reside at the centers of their host galaxies, where supermassive black holes have accumulated masses millions to billions of times greater than our Sun. These gravitational giants represent a distinct population from the stellar mass black holes born in supernova explosions, their origins tracing back to the earliest epochs of cosmic history through processes still debated by astrophysicists. Sagittarius A star, the supermassive black hole at the center of our own Milky Way, contains approximately 4 million solar masses, compressed within a region smaller than Mercury's orbit around the Sun. Its Schwarzschild radius spans roughly 12 million kilometers, yet this makes it a relative lightweight among galactic nuclei. The supermassive black hole in Messier 87, famously imaged by the Event Horizon Telescope in 2019, contains 6.5 billion solar masses, its event horizon stretching across a diameter larger than our entire solar system. TON 618, among the most massive black holes known, may contain 66 billion solar masses, its gravitational influence extending across a volume that could swallow the orbits of all planets out to Neptune several times over. The formation pathways for these cosmic behemoths remain subjects of active research. Direct collapse scenarios propose that pristine gas clouds in the early universe, lacking the heavy elements that promote efficient cooling and fragmentation, could collapse directly into black holes of 10,000 to 100,000 solar masses without first forming stars. These intermediate mass seeds would then grow through accretion and mergers over cosmic time. Alternative models suggest that the first generation of massive stars, forming from pure hydrogen and helium with masses potentially reaching several hundred solar masses, could have left behind black hole remnants that served as growth nuclei. The recent detection by gravitational wave observatories of black holes in the pair instability mass gap between roughly 65 and 120 solar masses hints at formation channels beyond simple stellar evolution. Regardless of their origins, supermassive black holes grow primarily through accretion of surrounding gas, a process that transforms them into the most luminous persistent objects in the observable universe. When sufficient fuel reaches the central engine, the resulting active galactic nucleus can outshine its entire host galaxy by factors of hundreds or thousands. The quasar 3C273, located roughly 2.5 billion light-years away, shines with an apparent magnitude of 12.9, bright enough to observe with amateur telescopes despite its enormous distance. Its intrinsic luminosity exceeds 4 trillion times that of our Sun, all generated within a region smaller than our solar system. The taxonomy of active galactic nuclei reflects the diverse orientations and accretion rates at which we observe these objects. Seyfert galaxies, first catalogued by Carl Seyfert in 1943, show bright, compact nuclei with distinctive emission line spectra, their central engines visible through relatively unobscured sight lines. Type 1 Seyferts display both broad emission lines, originating from gas clouds moving at velocities of several thousand kilometers per second within light days of the black hole, and narrow emission lines from more distant, slower-moving material. Type 2 Seyferts show only the narrow components, their broad line regions hidden behind obscuring tori of dust and gas that intercept our line of sight. Quasars represent the most luminous manifestation of active galactic nuclei, their name derived from their original classification as quasi-stellar radio sources due to their point-like appearance despite enormous distances. The discovery in 1963 that 3C273 possessed a redshift of 0.158, placing it at what was then an unprecedented distance, revolutionized understanding of extragalactic astronomy. These objects demonstrated that processes occurring near supermassive black holes could generate luminosities previously thought impossible, their energy output requiring accretion rates of several solar masses per year onto black holes of hundreds of millions to billions of solar masses. Radio-loud active galactic nuclei comprising roughly 10% of the population produce the powerful relativistic jets that inflate those megaparsec-scale lobes. The dichotomy between radio-loud and radio-quiet objects appears connected to black hole spin, with the Blandford-Zanarjek mechanism requiring significant angular momentum to efficiently extract rotational energy into jet power. Fanaroff-Riley classification divides radio galaxies into two morphological types based on their radio brightness distribution. FR1 sources show brightest emission near the core, their jets decelerating and spreading into diffuse plumes. R2 sources display edge-brightened lobes terminated by compact hotspots, where the jets impact the intergalactic medium, their higher jet powers maintaining collimation to greater distances. Blazers represent active galactic nuclei viewed directly down the jet axis, their emission dominated by relativistically beamed radiation from plasma moving toward us at speeds exceeding 99% of light speed. The Doppler boosting that results amplifies the observed luminosity while compressing the timescale of variability, allowing blazers to show dramatic brightness changes within hours or even minutes. BL Lacertae objects, named after the prototype initially misclassified as a variable star, display nearly featureless optical spectra, their emission lines overwhelmed by the beamed continuum from the jet. Flat-spectrum radio quasars show stronger emission lines, their jets viewed at slightly larger angles that reduce the beaming factor enough to reveal the underlying broad line region. The unified model of active galactic nuclei proposes that this apparent diversity reflects primarily orientation effects rather than intrinsic physical differences. A central supermassive black hole surrounded by an accretion disk, a broad line region of fast-moving clouds, a dusty torus at larger radii, and potentially a relativistic jet, can produce the full range of observed phenomena depending on the viewing angle. Face-on views through the torus opening reveal Type 1 Seyferts or quasars with their broad emission lines. Edge-on views through the obscuring torus produce Type 2 classifications. Jet-aligned sight lines yield blazars with their extreme variability and beamed emission. The torus itself, that obscuring structure of dust and molecular gas, maintains temperatures ranging from roughly 1500 Kelvin at its inner edge, where dust grains sublimate, to a few tens of Kelvin in its outer reaches. Infrared observations reveal this thermal emission, with the spectral energy distribution encoding information about the torus geometry and dust composition. Clumpy torus models, replacing earlier smooth distributions, better reproduce observed properties, with individual clouds of optical depth around 50 orbiting the nucleus at velocities of several hundred kilometers per second. Reverberation mapping exploits the light travel time across the broad line region to measure its physical size and, combined with velocity information from emission line widths, to weigh the central black hole. When the continuum emission from the accretion disk brightens, the broad emission lines respond after a delay corresponding to the light travel time from disk to clouds. For NGC 5548, one of the best-studied Seyfert galaxies, this delay spans roughly 20 light days, placing the broad line region at a distance of approximately 500 billion kilometers from the central black hole of 67 million solar masses. The relationship between supermassive black holes and their host galaxies reveals a profound connection between the smallest and largest scales of galactic structure. The M-sigma relation demonstrates that black hole mass correlates tightly with the velocity dispersion of stars in the galactic bulge, despite the black hole's gravitational sphere of influence extending only a tiny fraction of the bulge radius. A galaxy with stellar velocities averaging 200 kilometers per second typically hosts a black hole of roughly 100 million solar masses. This correlation implies that black hole growth and galaxy evolution proceed in lockstep, regulated by feedback processes that couple the nuclear engine to gas throughout the galaxy. That feedback manifests through both radiative and mechanical channels. Radiation pressure from luminous active nuclei can drive winds at velocities of thousands of kilometers per second, sweeping gas from the nuclear regions and potentially quenching star formation throughout the host galaxy. The mechanical energy deposited by relativistic jets inflates cavities in the hot gas halos of massive elliptical galaxies, preventing that gas from cooling and forming new stars. X-ray observations of galaxy clusters reveal these cavities as depressions in the surface, brightness, their enthalpy content reaching 10 to the 60 joules in the most powerful systems, sufficient to offset radiative cooling losses over hundreds of millions of years. The most violent events in the universe, paradoxically, announce themselves through the gentlest of messengers. While electromagnetic radiation from active galactic nuclei floods the cosmos with photons carrying energies from radio waves to gamma rays, another form of radiation propagates through the fabric of space-time itself, ripples in the geometry that Einstein predicted in 1916, but that would take a century to detect directly. Gravitational waves emerge whenever mass accelerates asymmetrically, but the weakness of gravity compared to other forces means that only the most extreme cosmic events produce waves strong enough to measure across astronomical distances. The mathematics of general relativity describes these waves as transverse perturbations in the metric tensor, oscillations that stretch space in one direction while compressing it in the perpendicular direction, then reverse, creating a characteristic quadrupole pattern that propagates at the speed of light. The amplitude of these waves, measured as a dimensionless strain representing the fractional change in length, decreases inversely with distance from the source, not as the inverse square that governs electromagnetic radiation intensity. Binary systems of compact objects provide the most powerful gravitational wave sources accessible to current detectors. Two neutron stars or black holes orbiting each other lose energy through gravitational radiation, their orbits shrinking as the waves carry away angular momentum. This inspiral proceeds slowly at first, the orbital period decreasing by imperceptible amounts over millions of years, but the process accelerates as the objects draw closer. The gravitational wave luminosity scales as the fifth power of the orbital velocity divided by the speed of light, meaning that the final moments of in-spiral release energy at rates that dwarf the electromagnetic output of entire galaxies. The Hulse-Taylor binary pulsar, discovered in 1974, provided the first indirect evidence for gravitational waves. This system consists of two neutron stars, one of which is a pulsar whose radio pulses serve as an exquisitely precise clock. Over decades of observation, the orbital period of 7.75 hours has decreased by approximately 76 microseconds per year, matching the prediction of general relativity for gravitational wave emission to within 0.2%. The two neutron stars, each with a mass of roughly 1.4 solar masses, will spiral together and merge in approximately 300 million years. But the gravitational waves they emit today carry power equivalent to about 7.35 times 10 to the 24 watts, roughly 2% of the sun's luminosity, radiated not as light but as ripples in space-time. Direct detection required measuring strains of 10 to the minus 21, a fractional length change so small that it corresponds to measuring the distance to the nearest star to within the width of a human hair. The Laser Interferometer Gravitational Wave Observatory, LIGO, achieved this sensitivity through a combination of extraordinary engineering and the fundamental physics of interferometry. Each of the two LIGO detectors, located in Hanford, Washington, and Livingston, Louisiana, consists of two perpendicular arms, 4 kilometers long, with laser beams bouncing between mirrors at each end. A passing gravitational wave stretches one arm while compressing the other, shifting the interference pattern of the recombined beams by a fraction of a wavelength. The mirrors themselves, weighing 40 kilograms each, hang from quadruple pendulum suspensions that isolate them from ground vibrations at frequencies above 10 Hertz. The laser light, initially at 20 watts, builds up to 750 kilowatts, circulating in the arm cavities through resonant enhancement. Quantum noise, arising from the discrete nature of photons, sets the fundamental sensitivity limit at high frequencies, while thermal noise in the mirror coatings dominates at intermediate frequencies. The entire system operates in an ultra-high vacuum of 10 to the minus 12 atmospheres, preventing air molecules from scattering the laser light. On September 14th, 2015, at 9:45 Coordinated Universal Time, both LIGO detectors registered a signal that would transform gravitational wave astronomy from theoretical prediction to observational science. The event, designated GW150914, began as a faint oscillation at 35 Hz, rising in both frequency and amplitude over approximately 0.2 seconds until it peaked at 150 Hz, then rapidly decayed. The waveform matched the theoretical template for two black holes spiraling together and merging, the frequency chirp encoding the masses of the objects and the amplitude encoding their distance. Analysis of the signal revealed that the two black holes had masses of 36 and 29 solar masses, significantly larger than any stellar mass black holes previously measured through X-ray observations of binary systems. Their inspiral brought them together at velocities reaching 0.6 times the speed of light in the final orbits, the gravitational wave frequency doubling every few cycles as the orbital period halved. At merger, the two event horizons touched and coalesced, forming a single black hole of 62 solar masses surrounded by a highly distorted horizon that rang down to equilibrium like a struck bell. The missing 3 solar masses, the difference between the sum of the initial masses and the final mass, converted entirely to gravitational wave energy during the final fraction of a second. This energy release, approximately 5.4 times 10 to the 47 joules, exceeded the combined electromagnetic luminosity of all stars in the observable universe during that brief interval. The peak gravitational wave luminosity reached 3.6 times 10 to the 49 watts, or about 200 solar masses per second converted to radiation, making GW 150914 momentarily the most powerful event in the universe since the Big Bang. The signal arrived at the Livingston detector 6.9 milliseconds before reaching Hanford, this time delay constraining the source direction to a ring on the sky. The strain amplitude of 10 to the minus 21 at Earth, combined with the inferred masses, placed the source at a luminosity distance of 1.3 billion light-years, corresponding to a redshift of 0.09. The gravitational waves had traveled for 1.3 billion years, passing through the expanding universe, while the light from the merger, if any electromagnetic counterpart existed, would have faded long before any telescope could have observed it. The ring-down phase following merger provided a direct test of the no-hair theorem, which states that black holes are completely characterized by only three parameters: mass, spin, and electric charge. The newly formed black hole, with a mass of 62 solar masses and a spin parameter of 0.67, settled to its final Kerr geometry through damped oscillations at frequencies and decay rates predicted by general relativity. The observed ring-down matched these predictions, confirming that the remnant behaved as a Kerr black hole rather than some more exotic compact object. Subsequent observing runs have detected dozens of binary black hole mergers, revealing a population of black holes with masses ranging from a few solar masses to over 80 solar masses. Some of these masses fall in the pair instability gap between roughly 50 and 130 solar masses, where stellar evolution theory predicted that supernovae should completely disrupt the star rather than leaving a compact remnant. The existence of black holes in this mass range suggests either hierarchical mergers of smaller black holes in dense stellar environments or modifications to our understanding of massive star evolution. The detection of GW 170817 on August 17, 2017, opened a new chapter in multi-messenger astronomy. This event, originating from a binary neutron-star merger at a distance of 130 million light-years in the galaxy NGC 4993, produced gravitational waves that swept through the LIGO and Virgo frequency bands over approximately 100 seconds, far longer than the fraction of a second black hole mergers. The slower in spiral reflected the lower masses involved, each neutron star weighing between 1.1 and 1.6 solar masses. Just 1.7 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same region of sky, confirming decades of theoretical speculation that binary neutron star mergers power these enigmatic explosions. The delay between the gravitational wave and gamma ray signals, after accounting for the different emission times during the merger process, constrained the speed of gravitational waves to equal the speed of light to within 1 part in 10 to the 15th, ruling out many alternative theories of gravity. The electromagnetic afterglow of GW 170817 evolved over days and weeks as the merger ejector expanded and cooled. Optical and infrared observations revealed the signatures of rapid neutron capture nucleosynthesis, the R process that forges elements heavier than iron. Spectroscopic analysis identified absorption features consistent with lanthanide elements like neodymium and europium, confirming that neutron star mergers contribute significantly to the cosmic abundance of heavy elements. The total mass of R process material ejected in this single event, approximately 0.05 solar masses, suggested that neutron star mergers could account for most of the gold, platinum, and uranium in the universe. The gravitational wave signal itself encoded information about the neutron star equation of state through tidal effects during the late inspiral. As the two neutron stars approached within a few hundred kilometers of each other, their mutual gravitational fields raised tidal bulges that extracted energy from the orbit, accelerating the inspiral beyond what point mass dynamics would predict. The magnitude of this tidal deformability depends on how stiff or soft the neutron star matter is, with stiffer equations of state producing larger, more easily deformed stars. Analysis of GW170817 constrained the radius of a 1.4 solar mass neutron star to between 10.5 and 13.3 kilometers, ruling out the stiffest proposed equations of state. Future gravitational wave detectors will extend the reach of this new astronomy to cosmological distances and lower frequencies. The space-based Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will detect gravitational waves at millihertz frequencies, opening a window on supermassive black hole mergers, compact binary systems in our galaxy, and possibly the stochastic background from the early universe. Pulsar timing arrays, which monitor the arrival times of radio pulses from millisecond pulses across the galaxy, have already detected evidence for a gravitational wave background at nanohertz frequencies, likely produced by the cosmic population of supermassive black hole binaries. The universe speaks in gravitational waves as surely as it speaks in light, and humanity has finally learned to listen. Yet even as gravitational wave observatories reveal the violent collisions of compact objects, a quieter revolution in understanding has emerged from the intersection of gravity, quantum mechanics, and thermodynamics. The question that sparked this revolution seemed almost philosophical when Jacob Bekenstein first posed it in 1972. Does a black hole have entropy? The classical view of black holes, derived purely from general relativity, suggested they were remarkably simple objects. The no-hair theorem, proven through a series of mathematical arguments in the 1960s and 1970s, established that a stationary black hole is completely characterized by just three quantities: its mass, its angular momentum, and its electric charge. All other information about the matter that formed the black hole, or fell into it afterward, seemed to vanish behind the event horizon. A black hole formed from the collapse of a star made of iron would be indistinguishable from one formed from hydrogen, antimatter, or library books, provided they shared the same mass, spin, and charge. This simplicity created a thermodynamic puzzle. The second law of thermodynamics states that the total entropy of an isolated system never decreases. Entropy, roughly speaking, measures the number of microscopic arrangements consistent with a system's macroscopic properties, or equivalently, the amount of information needed to specify the system's exact state. When matter falls into a black hole, its entropy seemingly disappears from the observable universe. One could, in principle, reduce the entropy of the external universe by throwing high-entropy objects into a black hole, apparently violating the second law. Bekenstein proposed a radical solution. He suggested that black holes themselves carry entropy, and that this entropy is proportional to the area of the event horizon rather than the volume enclosed. The Bekenstein-Hawking entropy formula, refined by Stephen Hawking's subsequent work, states that a black hole's entropy equals 1/4 of its horizon area, measured in Planck units. A Planck area, roughly 2.6 times 10 to the negative 70 square meters, represents the smallest meaningful unit of area in quantum gravity. For a black hole of 10 solar masses, with a Schwarzschild radius of approximately 30 kilometers, the horizon area spans about 11,000 square kilometers, yielding an entropy of roughly 10 to the 79th power in natural units. This exceeds the entropy of the star that formed it by many orders of magnitude. The assignment of entropy to black holes suggested they must also have temperature, since thermodynamic systems with entropy respond to energy input by changing temperature. Hawking's 1974 calculation confirmed this expectation in a startling way. By analyzing quantum field theory in the curved space-time near a black hole's event horizon, Hawking discovered that black holes are not perfectly black. They emit thermal radiation at a specific temperature inversely proportional to their mass. The mechanism underlying Hawking radiation emerges from the quantum vacuum itself. Empty space, according to quantum field theory, seethes with virtual particle-antiparticle pairs that constantly appear and annihilate. These fluctuations normally cancel out, contributing nothing to macroscopic observations. Near an event horizon, however, the intense gravitational field can separate a virtual pair before annihilation occurs. One particle falls inward, crossing the horizon, while its partner escapes to infinity as real radiation. The escaping particle carries positive energy, which must be balanced by negative energy falling into the black hole. This negative energy contribution reduces the black hole's mass, causing it to slowly evaporate. The temperature of Hawking radiation follows a precise formula. For a Schwarzschild black hole, the temperature equals the reduced Planck constant times the speed of light cubed, divided by 8p times the gravitational constant times the black hole mass times Boltzmann's constant. Substituting numbers reveals that a black hole of 1 solar mass would have a temperature of approximately 60 nanokelvins, or 60 billionths of a degree above absolute zero. This is far colder than the cosmic microwave background radiation, which bathes the universe at 2.725 Kelvin. Consequently, stellar mass black holes absorb more energy from the cosmic microwave background than they emit through Hawking radiation, causing them to grow rather than shrink in the current epoch. The temperature increases as mass decreases, creating a runaway process for sufficiently small black holes. A black hole with the mass of Mount Everest, roughly 10 to the 15th kilograms, would have a temperature of about 10 to the 11th Kelvin and would be emitting gamma rays. A black hole with the mass of a large asteroid would glow white hot. As the black hole shrinks, its temperature rises, accelerating the emission, which further reduces the mass, raising the temperature still higher. The final moments of black hole evaporation would release the remaining mass energy in a burst of high-energy particles and radiation. The timescale for complete evaporation depends on the initial mass cubed. A solar mass black hole would require approximately 10 to the 67th years to evaporate, a duration so vast that it exceeds the current age of the universe by 57 orders of magnitude. The universe would need to expand and cool for eons beyond imagination before stellar mass black holes began their final dissolution. Smaller black holes evaporate faster. A black hole with the mass of a small mountain would evaporate in roughly the current age of the universe, about 13.8 billion years. Primordial black holes of this mass, if they formed in the early universe, might be reaching the end of their lives now, potentially detectable as bursts of gamma radiation. The thermodynamic properties of black holes obey laws remarkably parallel to ordinary thermodynamics. The zeroth law states that the surface gravity of a stationary black hole is constant across the event horizon, analogous to temperature being uniform throughout a system in thermal equilibrium. The first law relates changes in mass to changes in horizon area, angular momentum, and charge, mirroring the conservation of energy. The second law, generalized by Bekenstein, states that the total entropy of black holes plus the entropy of matter outside never decreases. The third law suggests that the surface gravity of a black hole cannot be reduced to zero through any finite physical process, paralleling the unattainability of absolute zero temperature. These parallels run deep, suggesting that gravity and thermodynamics share fundamental connections not yet fully understood. The entropy formula implies that the information content of a black hole scales with its surface area rather than its volume, a property called holography. This hints that the true degrees of freedom describing a black hole, and perhaps space-time itself, reside on boundaries rather than in bulk regions. String theory and related approaches to quantum gravity have partially confirmed this picture, counting microscopic states of certain black holes and reproducing the Bekenstein-Hawking entropy exactly. The radiation emitted by black holes appears perfectly thermal, carrying no information about what fell in beyond the total mass, spin, and charge. This creates the information paradox. If a pure quantum state, such as a carefully prepared collection of particles, falls into a black hole, and the black hole subsequently evaporates completely into thermal radiation, the final state appears to be mixed rather than pure. Such evolution would violate the unitarity of quantum mechanics, a foundational principle stating that information is never truly lost, only scrambled. The resolution of this paradox remains one of the deepest unsolved problems in theoretical physics, touching on the nature of space-time, the fate of singularities, and the ultimate theory unifying gravity with quantum mechanics. The paradox deepens when examined through the lens of quantum field theory on curved space-time. Stephen Hawking's original 1974 calculation treated the gravitational field classically, while quantizing the matter fields propagating upon it. A semi-classical approximation that breaks down precisely where we need it most. Near the singularity, where space-time curvature approaches infinity, the separation between gravity and quantum mechanics becomes untenable. The Planck scale, defined by fundamental constants as approximately 1.6 times 10 to the negative 35 meters, marks the regime where quantum gravitational effects dominate. At this scale, the very notion of smooth space-time dissolves into something more fundamental, perhaps a quantum foam of fluctuating geometry, perhaps discrete building blocks of space itself. The information paradox sharpens into a trilemma, sometimes called the firewall paradox, articulated by Almheri, Marolf, Polchinski, and Sully in 2012. Consider an old black hole that has radiated away more than half its initial entropy. According to the principle of unitarity, the late Hawking radiation must be entangled with the early radiation already escaped to infinity, allowing information to be recovered by examining correlations in the complete radiation spectrum. However, for an infalling observer to experience nothing unusual at the event horizon, as general relativity predicts, the late radiation must also be maximally entangled with modes just inside the horizon. Quantum mechanics forbid such polygamous entanglement. A single quantum system cannot be maximally entangled with two independent systems simultaneously. Something must give. Either unitarity fails, or the equivalence principle breaks down at the horizon, or the interior geometry differs radically from classical expectations. The firewall proposal suggests that the entanglement with early radiation wins, severing the connection across the horizon and creating a wall of high-energy quanta that would incinerate any infalling observer. This violent departure from general relativity troubles many physicists, as it implies that quantum effects become important not at the Planck scale, but at the macroscopic scale of the event horizon, which for a supermassive black hole like Sagittarius A star extends some 12 million kilometers from the center. The curvature there is gentle, comparable to the tidal forces experienced in Earth orbit, yet the firewall would represent a discontinuity in the quantum state of space-time itself. String theory offers one framework for addressing these puzzles. In this approach, the fundamental constituents of nature are not point particles, but one-dimensional strings vibrating at different frequencies, with each vibrational mode corresponding to a different particle species. The theory naturally incorporates gravity, with the graviton emerging as a particular string excitation. Crucially, string theory provides a microscopic accounting of black hole entropy. In 1996, Andrew Strominger and Kamran Vafa calculated the entropy of certain extremal black holes, those carrying the maximum possible charge for their mass, by counting the number of string configurations that produce the same macroscopic properties. Their result matched the Bekenstein-Hawking formula exactly, suggesting that the entropy truly reflects microscopic degrees of freedom, just as the entropy of a gas reflects the number of ways to arrange its molecules. This counting relies on the ADS/CFT correspondence, proposed by Juan Maldacena in 1997, which posits an equivalence between a gravitational theory in anti-de Sitter space, a space-time with constant negative curvature, and a conformal field theory living on its boundary. The boundary theory contains no gravity, only quantum fields interacting according to well-understood rules that preserve unitarity. If the correspondence holds exactly, then any process in the gravitational bulk, including black hole formation and evaporation, must have a unitary description in the boundary theory. Information cannot be lost because the boundary theory is manifestly unitary. The challenge lies in understanding how the information escapes from the bulk perspective, how the correlations encoded in Hawking radiation emerge from the geometry of space-time. Loop quantum gravity takes a different approach, quantizing space-time itself rather than matter fields propagating upon it. In this framework, space consists of discrete quanta, with areas and volumes taking on quantized values. The smallest possible area is approximately the Planck area, about 2.6 times 10 to the negative 70 square meters, and the smallest volume is the Planck volume, roughly 4.2 times 10 to the negative 105 cubic meters. The singularity at the center of a classical black hole, where density becomes infinite, is replaced by a region of Planck-scale curvature, where quantum gravitational effects dominate. Some loop quantum gravity models suggest that the singularity is resolved into a bounce, with matter that collapses into a black hole eventually re-expanding into a new region of space-time, perhaps a white hole that releases the stored information. The Page curve, named after physicist Don Page, describes how the entanglement entropy of Hawking radiation should evolve if information is preserved. Initially, as the black hole emits radiation, the entropy of the radiation increases because each emitted quantum is entangled with its partner behind the horizon. However, after the Page time, roughly when the black hole has lost half its initial entropy, the radiation entropy should begin to decrease as the newly emitted quanta become entangled with the previously emitted radiation rather than with the shrinking black hole interior. The entropy eventually returns to zero when the black hole completely evaporates, indicating that the final state is pure. Recent calculations using the island formula, developed by Pennington, Schenker, Stanford, and Yang, along with Almheiri, Engelhardt, Marolf, and Maxfield, have reproduced the Page curve from gravitational path integrals, suggesting that the semi-classical approximation, properly applied, already contains the seeds of unitarity. The island formula modifies the standard prescription for calculating entanglement entropy in the presence of gravity. It instructs us to extremize a generalized entropy functional that includes not only the von Neumann entropy of matter fields in a region, but also the area of certain surfaces called quantum extremal surfaces, divided by 4 times Newton's constant. Remarkably, after the Page time, the dominant contribution comes from an island, a region inside the black hole that is geometrically disconnected from the radiation, but contributes to its entropy. The information about what fell into the black hole is encoded not in local correlations near the horizon, but in subtle, non-local correlations that span the entire radiation field. These developments suggest that space-time itself may be emergent, woven from quantum entanglement between microscopic degrees of freedom. The ER equals EPR conjecture, proposed by Maldacena and Susskind, posits that entangled particles are connected by microscopic wormholes, Einstein-Rosen bridges linking distant points in space-time. If true, the geometry of space-time reflects the pattern of quantum correlations in an underlying state, and the smooth fabric of general relativity emerges only in a coarse-grained limit where individual quantum connections blur together. The black hole interior, from this perspective, is not a region of space that can be localized independently, but rather a collective phenomenon arising from the entanglement structure of the Hawking radiation and whatever fell in. The quest for quantum gravity extends beyond black holes to the earliest moments of the universe. At the Planck time, approximately 5.4 times 10 to the negative 44 seconds after the initial singularity, the entire observable universe was compressed into a region smaller than the Planck length. Classical general relativity cannot describe this epoch, as quantum fluctuations in the geometry become comparable to the geometry itself. A complete theory of quantum gravity would illuminate not only the fate of information in black holes, but also the origin of space-time, the selection of initial conditions, and perhaps the values of fundamental constants. The temperature at the Planck time was approximately 1.4 times 10 to the 32 Kelvin, hot enough that all four fundamental forces may have been unified into a single interaction. Such extreme temperatures and densities in the primordial fireball created conditions that may never again exist in the observable universe. Conditions where the formation of black holes required no stellar collapse, no supernova explosion, no gradual accumulation of matter over billions of years. In this earliest epoch, black holes could have formed directly from the fabric of space-time itself, born from density fluctuations in the hot plasma that filled all of existence. The mechanism relies on a simple principle that connects quantum mechanics to gravitational collapse. During the inflationary epoch, which lasted from approximately 10 to the negative 36 seconds to 10 to the negative 32 seconds after the initial singularity, the universe expanded exponentially, doubling in size roughly every 10 to the negative 37 seconds. This expansion stretched quantum fluctuations in the inflaton field, the hypothetical scalar field driving inflation, to macroscopic scales. These fluctuations became frozen into the fabric of space-time as regions of slightly higher and slightly lower density, seeds that would eventually grow into galaxies and galaxy clusters through gravitational instability. Most of these density perturbations were small, with amplitudes of roughly 1 part in 100,000, as measured by the cosmic microwave background radiation. These gentle ripples grew slowly over cosmic time, requiring hundreds of millions of years to collapse into the first stars and galaxies. But the spectrum of primordial fluctuations may have contained rare outliers, regions where the density contrast was far more extreme. If a region of the early universe contained enough excess mass within its own Schwarzschild radius, it would collapse directly into a black hole before any other structure could form. The critical threshold for primordial black hole formation depends on the equation of state of the universe at the moment of collapse. During the radiation-dominated era, which lasted from the end of inflation until approximately 47,000 years after the initial singularity, the pressure of the relativistic plasma resisted gravitational collapse. A density perturbation needed to exceed a threshold of roughly 0.45, meaning the local density had to be at least 45% higher than the average for collapse to proceed. This threshold made primordial black hole formation relatively rare, but not impossible. The mass of a primordial black hole is determined by the horizon mass at the time of formation, the total mass contained within the cosmological horizon at that moment. At the Planck time, this horizon mass was approximately 10 to the negative 5 grams, the Planck mass itself. A black hole forming at this instant would have been unimaginably small, with a Schwarzschild radius of roughly 1.6 times 10 to the negative 35 meters. Such a tiny black hole would have evaporated through Hawking radiation in approximately 10 to the negative 40 seconds, too brief to leave any lasting trace. But as the universe expanded and cooled, the horizon mass grew. At 1 microsecond after the initial singularity, the horizon mass had increased to approximately 1 solar mass. A primordial black hole forming at this epoch would have a mass comparable to a stellar mass black hole, yet it would have formed without any star, without any nuclear fusion, without any supernova. At 1 second after the initial singularity, the horizon mass reached roughly 100,000 solar masses, comparable to intermediate mass black holes that remain difficult to explain through conventional stellar evolution. And at the epoch of matter radiation equality, approximately 47,000 years after the initial singularity, the horizon mass had grown to roughly 10 to the 17th solar masses, far exceeding any black hole observed in the universe today. This relationship between formation time and mass creates a remarkable possibility. Primordial black holes could span an enormous range of masses, from the Planck scale to billions of solar masses, depending only on when they formed. The spectrum of primordial black hole masses would reflect the spectrum of density fluctuations in the early universe, providing a fossil record of conditions that existed long before any light we can observe was emitted. The survival of primordial black holes to the present day depends critically on their initial mass. Hawking radiation causes black holes to evaporate at a rate inversely proportional to the square of their mass, meaning smaller black holes evaporate faster. A black hole with an initial mass of approximately 5 times 10 to the 14th grams, roughly the mass of a small asteroid, would have a lifetime equal to the current age of the universe, approximately 13.8 billion years. Such a black hole would be completing its evaporation now, releasing a final burst of high-energy gamma rays as its temperature climbed toward infinity. Primordial black holes with initial masses below this threshold have already evaporated completely, their mass converted entirely into radiation through the quantum process Hawking discovered. The evaporation of these small primordial black holes in the early universe would have injected energy into the primordial plasma, potentially altering the abundances of light elements produced during Big Bang nucleosynthesis. Observations of helium-4, deuterium, and lithium-7 abundances place constraints on the number of primordial black holes that could have evaporated during the first few minutes of cosmic history. Primordial black holes with initial masses above 5 times 10 to the 14th grams would still exist today, slowly evaporating but far from complete destruction. A primordial black hole with a mass of 10 to the 15th grams would currently have a temperature of approximately 10 to the 11th Kelvin, emitting gamma rays with energies of roughly 10 mega-electron volts. The Fermi Gamma Ray Space Telescope has searched for the diffuse glow that a population of such evaporating primordial black holes would produce. finding no excess above the expected astrophysical backgrounds. This null detection limits the abundance of primordial black holes in this mass range to less than approximately 10 to the negative 8 of the total dark matter density. The constraints become weaker for more massive primordial black holes, which evaporate too slowly to produce detectable radiation. A primordial black hole with a mass of 10 to the 20 grams, roughly the mass of a small moon, would have a current temperature of only about 10 to the 6th Kelvin, emitting primarily in the X-ray band at an extremely low luminosity. Such objects would be nearly invisible to electromagnetic observations, detectable only through their gravitational effects. This invisibility has made primordial black holes intriguing candidates for dark matter, the mysterious component that constitutes approximately 27% of the universe's energy density. Unlike particle dark matter candidates, such as weakly interacting massive particles or axions, primordial black holes require no new physics beyond general relativity and the standard model of cosmology. They would interact with ordinary matter only through gravity, clustering in galactic halos and contributing to the gravitational potential that holds galaxies together. The gravitational lensing of background stars provides one method to search for primordial black holes in the dark matter mass range. When a compact object passes between Earth and a distant star, its gravity bends the starlight, causing the star to brighten temporarily in a characteristic pattern called microlensing. Surveys monitoring millions of stars in the Magellanic Clouds and the galactic bulge have detected thousands of microlensing events, most caused by ordinary stars and stellar remnants. The duration of a microlensing event depends on the mass of the lens, with primordial black holes in the range of 10 to the negative 7 to 10 solar masses producing events lasting from hours to months. The Eros and Macho collaborations conducted extensive microlensing surveys in the 1990s and 2000s, finding that primordial black holes cannot constitute more than approximately 10% of the dark matter if their masses lie between 10 to the negative 7 and 10 solar masses. More recent surveys by the Subaru Hypersuprime CAM have extended these constraints to lower masses, ruling out primordial black holes as the dominant dark matter component down to approximately 10 to the negative 11 solar masses, roughly the mass of the Moon. Yet windows remain open. Primordial black holes with masses near 10 to the negative 12 solar masses, or in the range of 10 to 100 solar masses, remain viable dark matter candidates, though increasingly constrained by various observations. The detection of gravitational waves from merging black holes by LIGO and Virgo has added new data to this question. Some of the detected black holes have masses that are difficult to explain through conventional stellar evolution, particularly those in the range of 30 to 50 solar masses, where pair instability supernovae should prevent black hole formation. Could these anomalous masses represent primordial black holes formed in the first second after the Big Bang, now merging billions of years later? The question remains open, a tantalizing possibility that connects the earliest moments of cosmic history to observations made in the 21st century. But whether primordial or stellar in origin, every black hole faces the same ultimate fate: The universe grants no exemptions from the laws of thermodynamics, and Hawking radiation ensures that even the most massive black holes will eventually surrender their existence to the quantum vacuum. The timescales involved stretch comprehension to its limits, yet the physics remains inexorable. Consider a stellar mass black hole of 10 solar masses, formed from the collapse of a massive star. Its Schwarzschild radius spans approximately 30 kilometers, and its Hawking temperature measures a mere 6 billionths of a Kelvin, roughly 6 times 10 to the negative 9 Kelvin. At this temperature, the black hole radiates energy at an almost imperceptible rate, losing mass so slowly that the process defies meaningful description. The evaporation time for such an object calculates to approximately 10 to the 67th years. Written out, this number contains 67 zeros, a duration so vast that the current age of the universe, 13.8 billion years, represents less than a single heartbeat in comparison. During this unimaginable span, the universe itself will transform beyond recognition. Stars will exhaust their nuclear fuel, galaxies will disperse, and even protons may decay if certain grand unified theories prove correct. The black hole persists through all of this, a patient remnant of an era when matter still clumped together and stars still burned. Supermassive black holes face even longer sentences. Sagittarius, a star, with its 4 million solar masses, will require approximately 10 to the 87th years to evaporate completely. The black hole at the center of Messier 87, weighing 6.5 billion solar masses, extends this timeline to roughly 10 to the 100th years. A Google years, a number that mathematician Edward Kasner's 9-year-old nephew coined in 1920 without any conception of the cosmic processes it would one day describe. As the universe ages, the cosmic microwave background radiation continues to cool. Currently at 2.7 Kelvin, this relic radiation from the Big Bang will eventually drop below the Hawking temperature of stellar mass black holes. When this occurs, black holes will finally begin losing mass faster than they absorb energy from their surroundings. The crossover point for a 10 solar mass black hole arrives when the cosmic background temperature falls to approximately 6 billionths of a Kelvin, an event that will occur roughly 10 to the 19th years from now. The evaporation process accelerates as mass decreases. A black hole's temperature rises inversely with its mass, meaning that as it shrinks, it grows hotter, radiating more intensely and losing mass more rapidly. This creates a runaway process in the final stages. When a black hole's mass drops to approximately 1 million kilograms, roughly the mass of a small asteroid, its temperature reaches 10 to the 13th Kelvin, hotter than any stellar core. Its remaining lifetime at this point measures only about 1 second. The final moment arrives with explosive intensity. In the last tenth of a second, the black hole releases approximately 10 to the 22nd joules of energy, equivalent to a 1 million megaton nuclear explosion. The Hawking radiation in these final instants includes not just photons, but all particle species whose rest mass energy falls below the black hole's temperature. Electrons and positrons stream outward, followed by muons, pions, and eventually quarks and gluons as the temperature climbs through 10 to the 12th Kelvin and beyond. What remains after this final burst? the question touches the deepest mysteries of physics. If Hawking's original calculation holds exactly, the black hole simply vanishes, leaving behind only the radiation it emitted during its long evaporation. The information that fell into the black hole over billions of years, the quantum states of every particle that crossed the event horizon, would be lost forever, erased from the universe in apparent violation of quantum mechanics. Yet most physicists now believe that information somehow escapes, encoded in subtle correlations within the Hawking radiation. The page time, named after physicist Don Page, marks the moment when a black hole has radiated away half its initial entropy. After this point, the emitted radiation must begin carrying information about the black hole's interior if unitarity is to be preserved. For a stellar mass black hole, the page time occurs approximately halfway through its evaporation. After roughly 10 to the 66th years, the entropy of a black hole, proportional to its horizon area, represents the maximum information that can be stored within a given region of space. A 10 solar mass black hole possesses an entropy of approximately 10 to the 79 in natural units, corresponding to roughly 10 to the 79 bits of information. As the black hole evaporates, this information must somehow transfer to the outgoing radiation, a process whose mechanism remains one of the great unsolved problems in theoretical physics. The universe after black hole evaporation enters what physicists call the dark era. No stars burn, no compact objects remain. Only a thin soup of electrons, positrons, neutrinos, and photons, all drifting apart as space continues to expand. The temperature approaches absolute zero asymptotically, and the density of matter drops below 1 particle per volume, equal to the current observable universe. In this ultimate darkness, thermodynamic equilibrium gradually establishes itself. The entropy of the universe approaches its maximum value, and no further macroscopic change becomes possible. This state, sometimes called heat death, represents not a dramatic ending, but a gentle fading, a universe that has exhausted all possibilities for transformation. Yet even here, quantum mechanics permits rare fluctuations. Over timescales of 10 to the 10 to the 50 years and beyond, random quantum events could theoretically assemble complex structures from the void, a phenomenon known as Boltzmann fluctuations. Whether such fluctuations have any physical significance, or whether they represent merely mathematical curiosities, remains debated. The black holes that once powered quasars, that bent space-time into impossible geometries, that swallowed stars and emitted gravitational waves across the cosmos, will have returned their borrowed mass energy to the universe. The information paradox may find resolution in theories not yet conceived, or in experimental evidence not yet gathered. For now, the physics of black holes and neutron stars stands as humanity's deepest probe into the nature of gravity, matter, and space-time. A story written in the language of mathematics and read in the light of distant X-rays, the ripples of gravitational waves, and the patient ticking of pulsars across the galaxy.